Hello, everyone, and welcome to the final session, the fourth and final session of Share Your Green Design, digital tools for the market for green building designs webinars. And this session will be on whole life carbon, the second session on this, part two. So in the first part, following up on the first session on whole life carbon, where we did an introduction to embodied carbon and operational carbon, as well as carbon which is involved in the whole life cycle of buildings. So just to give an overview of what we'll be expecting today, we will have the presentations from Andrea Ruíz from Atelier. Patrick Kavanagh will, from BDP will also give a presentation, after which we'll have a 15-minute Q&A on both presentations. After that, we'll take a 10-minute break. From then on, we'll pick up with the second set of presentations, first from Noella Nibakuze, excuse me, from Mass Design Group, as well as a presentation from Brunette from ARUP. After that, we'll have a final Q&A, another 15-minute Q&A for both presentations, and closing remarks, not just for this session, but also for the entire series. I hope you are as excited as we are to be able to have gone through all the 4 sessions all the way to the end. And without any further ado, I will hand you guys over to Andrea Ruíz. And as she comes on also, I'd like to remind you, if you have any questions, you can drop them on the chat section of the live feed, and we'll be able to address those questions at the Q&A. So welcome, Andrea.
Thank you very much, Louis. Really glad to have the opportunity to be presenting for you today and to share with all the speakers of these webinar sessions. Today, I'm going to give you an introduction to MEP services. So as you mentioned, we have already discussed about digital tools for green buildings in a very broad area about whole life carbon. And the intention is for me to give you a bit more details on how MEP services can impact on these calculations. With that said, I'm going to give you a bit more of information about myself. I'm part of the Atelier 10 team, who is a building services consultancy focused on the design of mechanical, electrical, public health, fire and lighting services, as well as the analysis of the environmental impact of them in buildings, as well as I'm part of the Share Your Green Design team, being one of the business and technical advisors. The agenda for today, for this presentation, is to kind of give you a history of the frameworks that we have seen in the UK, as I am currently working from the UK. But please keep in mind that the intention is to kind of see the approach of how this needs to be developed all throughout the world on international projects. I'll give you a description about CSTI and 65, which was issued in 2020, and then some rough estimations of what the MEP embodied carbon could do. Furthermore, the main message I want to give you is how could we make a difference on this, and then that can then be applied to how we use either TN65 or any other method. So let's start with the history of frameworks and standards. BSEN 5978 is the framework that was created for the assessment of the environmental performance of buildings. So this was created quite a long time ago, and it is very broad, as it talks about all of the parts of a building, including facades and structure. Now, there is another document that was issued by Ruíz that describe the process in a bit more detail. It helps to coordinate the calculations in a way that makes it standard and the way a bit more comparable. So this is the whole life carbon assessment for the built environment that they issued in 2017. And this definitely describes a bit more how those separations of the embodied carbon are described and how could we calculate them. Now, again, this still refers more to the general aspects of how to do this for all the parts of a building, and it has been well received. The other document I have here for you, which is the CSTI 65 issued in 2020, that provides a consistent approach for data and for the manufacturers to put together information about their embodied carbon and about their efforts to provide the client with the required idea. The CSTI 65 includes parts of the complete calculation, but not all. So let's look at them here. A whole life carbon, which is what we're trying to do at the end of the day. We're trying to define how all of the items that we put into the building, how we use them throughout the lifespan of the structure, and then how we discard them or leave them for beyond the life cycle. That reuse and recovery is a complete step. What TM65 focus on is more about the key part of the beginning of the stages. Whenever we are selecting equipment that will be probably there for quite many years, even though there is a replacement of some of them, it will actually make the primary source of the embodied carbon for the building. So these stages we have seen earlier, they go in the UK, they're named from A to D, and they include the details of the product, where it's coming from, how it was constructed, how is it used. Then the whole life carbon should include the operation and end of life, and then how to recover it. Now, the CIPSE excludes the part of the replacement or the refurbishment of that specific product, and it excludes the operational carbon, which is everything related to the building in a specific. So for how many years is that building going to be there? How many times do we need to replace that equipment? And how much energy is it required to make it run? So what we see here over on the other area, the blue area, is what CIPSE actually focuses on. So I do want to highlight also another image from the guide, which is over here on the right, that explains how actually the first part of the calculation includes the majority of the embodied carbon. So it is mainly about identifying what that product is, what are the materials within it, and that can definitely lead to how will be the final whole life carbon of the MEP services. One more thing is that I want to mention that we generally measure these on kilograms of CO2 equivalent per square meter of the EIA of the building we're working with. So this kind of gives us the set point and the strategy of how to approach the calculation, keeping in mind that it's at the beginning where we have the capability and the opportunity to make the biggest impact. So estimate about embodied carbon are a question that happens very often, and I must say that as the world is adapting and getting closer to sharing this information and making sure that the buildings are comparable with each other, then there has been a bit more data. Now, I'm presenting you here with a report that was developed by Skanska, and they have in the past on calculation. It was a calculation with representing quite a few buildings and modeling how they will operate, and then identifying both the MEP, mechanical, electrical, plumbing for the services, and also the tenant improvements. Although we may skip that subject for the meantime, but that mainly refers to what the tenant is actually applying for its specific floor or area. So if we see the figure 2 that they present on this report, it shows 3 different scenarios: low, medium, high, let's say, intensity of the embodied carbon of that building, and it ranges between 40 and 75. That is in kilograms of CO2 equivalent per square meter. Now, it is pretty important to highlight that it doesn't include the refrigerants. The refrigerants are volumes that are contained within the either heating, cooling, mainly equipment of a building, and they can really lead to high impacts on the embodied carbon. And it also does include some fixtures and fittings. Hence, this is just, let's say, our basic, maybe for now, to kind of have an idea of how they could be. Now, one more thing that is highlighted on this report is that even though there is a specific value at the beginning of the building with all those services we're bringing, in reality, because they need to be replaced, we will have to increase the amount of embodied carbon throughout the operation of the building. So that's what this image on the right wants to highlight. So I have limited it to the high estimate, but let's say, for example, that every 15 years you will have to replace some or all of the materials that you have in your building in relation to the equipment or distribution. Then if we do that for an example of a 60-year building lifespan, then we can see how the MEP does have a bigger impact. It does have an effect that is not necessarily discussed during the beginning of the design. So that's the project that we need to have, the prospects of how is it that we're going to be impacting this building for the future years. Yes, so that now that we have seen an idea of how the estimates of embodied carbon could be for MEP, we'll jump onto how could we make a difference? How could our design ensure that we make our best to have a low embodied carbon? So please note that this is in nowhere form something that is specifically described on any of the guides. This is just an idea what I want to bring to you. So I have, let's say, summarized this in 4 key actions, and those are listed next. So mitigating the refrigerant impact, then selecting the equipment uh, in quantity as small as possible, prioritizing those materials with low embodied carbon, and emphasizing on how durable this will be. So let's describe this a bit more. Over here, I'm giving you an example of some of the services that we could have in a building and how we, for each of them, will have to have that analysis. So with the first one, mitigating refrigerant impact. There can be many passive measures that can be taken throughout the design to avoid using as much as this as possible. But at the same time, it's about the type of refrigerant that we use that will make the final impact. So there in the guide of TM65, there's an example of quite a few of them, and if not, they can be researched outside. But over here, I'm listing for you a few examples of what could be a good embodied carbon material, such as R1234YF or ZE, propane, CO2, ammonia, and water. They are examples. Obviously, the industry is still changing and still adapting to these requirements about embodied carbon on buildings. So it might be something that we need to drive as designers or as part of the design team and part of the client side, which type of refrigerant are we using, and then follow with those suppliers that are adapting themselves as well. So one of the examples that we see on the image in the center, which is an idea of what is could be a high, medium, or low scenario of how that refrigerant could be selected. If we select one with a high impact, and then they have a high leakage rate, they could really imply high levels of CO2 equivalent throughout the process of the operation of the building. So even before we start selecting all of the materials of the building, just concentrating our time a little bit on what kind of refrigerant we're using will make a big change to the future. The next one is selecting as little equipment as possible, which obviously is something that we always try to achieve. But the intention there is to bring the entire design team to be part of this, to be part of the solution, and to define how could we adapt the building to enhance this. So limiting what we are heating and cooling plan, our ventilation plan throughout the distribution, pipework and ductwork, electrical, could be the generation and or distribution of services, lifts, etc. And then obviously we will have this on the main planters of the building, but at the same time, depending on how many floors we have, the on-floor distribution will also make an impact here. So specifying equipment with low, let's say, embodied carbon through a calculation will really help. Then prioritizing the equipment with low embodied carbon. Obviously, we may have the opportunity to do this in more when we select specific materials, like for example, all the ductwork of an office or a commercial building, or all the pipework that has quite a lot of mass, hence it will have a big effect. So CIPSE has guidance in terms of some of the of these values, and some of the components I'm listing for you here are the highest ones. For example, electronic components and printing wiring boards, they have a quite a really high impact, although they're, because of their quantities, they might not really make such a big difference. Well, steel and well, aluminum is actually quite high as well, so I wanted to highlight that. So if we have, let's say, a large part of our design that is developed with units that are made out of aluminum, then they will definitely create an implication later on. Finally, listing in here for you the durability. So even though in the C1765 we skip the part of how many times do we replace the equipment, this will be used at the final end value of the whole life carbon. So an example of this could be having an idea through the CIPSE Guide M, or other guys used in other parts of the world for the lifespan of an equipment. So all I'm trying to say is that if we have units that we know that will need to be replaced in 10 or 20 years, we will need to at the end account for them as many times they are required until we complete the lifespan of the building. So if we focus from the beginning on using as design that is durable and that makes it maybe is a system that lasts longer, then that will always have a welcome part on the on the project team to meet these requirements. So yes, we have gone through all the 4 key actions that I wanted to share with you to have in mind before we start even calculating the embodied carbon of the MEP services. So now we'll jump onto the CIPSE guide, TM65. So it does have 2 methods. I'm describing here for you the basic approach mainly, just to give you an example of what it is. This is used mainly when there is no much data from the suppliers and is really helping the industry at the moment, because when the suppliers do not have a detailed description, they can still share with us how much is the weight of the product and how is the material breakdown in terms of how much is the percentage that that specific equipment has in terms of, let's say, for example, material 1 steel, material 2 aluminum. That way, with just that information, we can already have our projections of what the embodied carbon for that product will be. So there's furthermore details about what this guide is trying to give us, but in reality is helping to make sure that this calculation can be done at the beginning of the project when there is not that much guide or defined services, or as well whenever we don't have detailed information from suppliers, which hopefully will increase in the future. So yeah, over here we have an example. We will have, let's say, in step 1, the kilograms of the system multiplied by the embodied carbon of that material. Then we will add a 10% to that to calculate A1 to B3. Then for a specific type of services, which will depend on how complex they are, we will allow for a scale-up factor, and then we will also add to this a buffer factor just because of the implications of how simple this method is. So yeah, there is a second method called, let's say, medium level, the mid level, and it's a bit more descriptive, because if we have more details from the supplier, then it's even better. The good thing about the CIPSE guide is that it has given a form and that you can share with the suppliers, and hopefully they can help standardize their responses, so they can give almost everybody the same information. And finally, obviously, once you have all the products, you still need to add the refrigerant leakage, which we discussed earlier, which could have a big impact. So that's mainly the guide, and once we have this, we still need to sum all of the services and then arrive to our whole life carbon. Now, there is an even better approach if we have a connection with the supplier, or if we research online how to find this. And this is the Epd approach. So it's actually a standard that has been created for a while, and an Epd is the environmental product declaration. I'm giving you an example here about how this document will provide information of the different stages of the product that we have. So it's much more detailed. let's say it has A1 to A5, C1 to C2, C3, C4, and with this we will be able to have a better understanding of the embodied carbon. There is not that additional background or scale of factor, so it will be closer to the to the whole life carbon that we need. It is important to say that an environmental product declaration have, I believe, a lifespan of 5 years, and that means that in order for a manufacturer to do this, they'll need to describe where the product is manufactured, how is it arriving, all of their materials to site, and the energy or all of the items required for that product to be created. So obviously, depending on time, this will vary, and it will be more impactful, hopefully a lower EPD, a lower whole life carbon effect on what we see from the billing, hopefully. So yeah, the actual document is quite long, and we will need to identify what is the GWP of that specific product, and obviously the CSTI guide not only help us to understand the EPDs can be used, but also to read the EPDs correctly and to define which values to associate with our basic or medium approach so we can sum them all together. Finally, what I have here for you is an idea of the sources that can be used. This is for various countries, and an additional detail will need to be reviewed in case you are in a different country, just because it might take longer transportation for it to arrive to where you are located, etc. So the example I have here in terms of association is the Eco Platform EPD Verified, which is like an international or a European congregation of different certifications, and you will probably see this logo on various EPDs that you receive. And the intention is that they're making sure that this is standardized within all of the different associations that provide the EPDs. This is a acronym in English, but obviously you have a different acronym in other languages. Now you will see maybe something called PP from France, or there is a website from the Institute Bowen on World EV, and I'm sorry for my accent in this German institution, that will also be providing various units. And as well from Sweden, we have the International EPD system. So if we would like to find online some of the EPDs we can, there is a possibility to reach out if we are working in our calculations already online with their support. And hopefully this database will be growing as more suppliers connect to the system. In addition to this, I have a few examples here, not just this, but there are many others who already have in their websites the EPDs for their products, or for some of them. So we can go to them. For example, we can see insulation, air handling units, chillers with the on EPD that can be used as a guidance whenever we are in this process. So I hope this information has been helpful. Please keep in mind that once you see the guide, you will need to adapt it to where you are. There might be one specific to your country, but still, I will envisage that using EPDs or PPs or any acronym for this document will be the general approach to getting closer to the value. Thank you very much. That was mainly the information I wanted to share with you, and I'm looking forward to any more questions.
Okay, thank you very much, Andrea, for that presentation. Patrick, we'll have you come in next. Just a reminder to have your questions ready for the rest of the guys on the YouTube live feed. And without further ado, we'll hand you over now to Patrick.
Thanks, Ruíz. Hi, guys. Thanks for having me here. It's great to be involved. So today, I'm going to give a presentation intended to give you some insight into the types of digital tools we utilize here in BDP's engineering team, and how we use them to design and innovate with the ultimate goal of producing a sustainable building. I'll also touch on some of the specific engineering strategies that we have implemented on our recent projects and how these tools help deliver them. So to start with, I'll just introduce myself. My name is Patrick Kavanagh, and I'm an engineering associate with BDP. I'm a chartered building services engineer and graduated from the Technical University of Dublin. I suppose I graduated as a building services engineer many years ago and had an initial kind of thrown into pipes and ducts and sizing pumps and chillers and things like that. And really my sustainability journey then started about 11 years ago after I moved to Australia looking for work during the downturn here in Europe. I now am back in Ireland in Dublin leading BDP sustainability team, and throughout the last number of years I've collected a number of sustainability accreditations over my time. So these include I'm a BREEAM accredited professional, I'm a lead green associate, WELL AP, I'm a building energy rating assessor, a display energy cert assessor, I'm an energy auditor for SEAI, and I'm actually an external examiner for the Technical University of Dublin as well. So just very briefly to kind of introduce BDP and who we are. So BDP, we're an international multidisciplinary design practice, and last year celebrated 60 years of design and 30 years in Ireland. We have approximately 1,000 architects and engineers worldwide, providing the full range of specialisms from architecture, building services, civil structural, sustainability, to name a few. We're known as leaders in sustainable design, and our team in Dublin has won 35 awards within the last 10 years in relation to sustainability. We've written over 40 articles and research papers, and we're regularly called as expert speakers and lectures in sustainability. What we like to do is carry out kind of research on projects we've completed or in design, and this feeds into our unique innovation and insights. And we're involved in all of the building industry sectors, from commercial offices right through to residential developments. So by way of introduction to this presentation, my approach is to, I suppose, step through it the same way we would step through a design, looking at the design hierarchy. So to start with, we're going to look at some of the digital tools and concepts for passive design. So looking at solar and daylight studies, facade analysis and building form, the use of macro flow, thermal mass, and embodied carbon analysis. For our active design then, I'm going to touch on some of the innovative HVAC designs that we've utilized on some of our recent projects here in Dublin. That will kind of lead me into, a small piece on BIM coordination, how we use CFD analysis of airflows for specific applications and design. I'll touch briefly on Dilux, just the lighting analysis tool we use, and ProDesign, which is used for electrical cable sizing. And to finish off my presentation, I'm going to speak about the innovative use of renewables and some of the constraints associated with them, controls and water conservation measures we've adopted, and lastly then just BMS monitoring after handover, which is something that we try to get involved in where the clients allow us. So to start with passive design. So with solar and daylight studies, I suppose a typical element of our scope, I'd say, and probably 80 to 90% of our projects, whilst we look after kind of building services, we would also be scoped to carry out daylight, sunlight, and overshadowing impact assessments. So, this is normally carried out initially at the planning stage, because if you don't get it right at planning stage, then your building form, glazing ratios, the impact on neighbours is something you find very hard to change post-planning. So the guidelines that we typically have to work to or meet would be the BRE 2009 Sunlight Layout Planning for Daylight and Sunlight, which actually had a third edition released just 2 weeks ago. We work to the British Standard A206 Code of Practice for Daylighting, the recently released EN 17037 methodology, and the CIBSIA LG10. So if we start with the solar analysis, the software we use for solar and daylight studies in BDP at least is IES Virtual Environment, specifically the radiance and suncast applications in the software. So we model and analyze the annual probable sunlight hours before and after development and review the vertical sky component, measuring how existing windows to neighbouring dwellings are impacted. BRE 2009 guidance requires the sunlight hours will be 25% of the annual probable sunlight hours, and for the vertical sky component be greater than 0.27. And post-development, a loss of greater than 20% is typically considered in planning circles to result in a noticeable loss of sunlight. So that's kind of our threshold and target that we try to be under. We also use the software for overshadowing studies. So, you know, we look at the massing of the building with the architects, and this helps inform what impact it's going to have on both kind of neighboring properties, but we also test the shadow cast by those new developments and its impact on direct sunlight for outdoor amenity spaces, playgrounds, public streetscapes, and private gardens. So the guidance recommends that at least 2 hours of direct sunlight is achieved on 50% of the area on the 21st of March. And the 21st of March is used because this is the average sun path for the year. So it gives you kind of the average of where that shadow is going to be cast. Obviously during the summer months, the sun is higher in the sky, and so the shadow would be lesser, and in the winter months there'd be a greater shadow cast. Again, with shadow casting and overshadowing, generally it's kind of looked at that if there's more than a 20% difference, then that can be kind of noticeable to somebody. And then with daylight assessments, so we use IES radiance to carry out daylight assessments within new developments, and these are benchmarked against various industry targets depending on the use. So, for example, an office space may seek 2% average daylight factor for 80% of its floor area to meet a BREEAM credit requirement. Or if we're looking at complying with the EN 1737 requirement, then we'd be looking at radiance to establish the lux levels of bedrooms and kitchen living rooms in dwellings. We would use radiance as a daylight modeling tool to assess the daylight within apartments to meet planning requirements very, very regularly, because this has become, particularly in Ireland, a very contentious issue and something that every planning authority is looking for. So, you know, recently, I would say in the last 18 months, anyone who's working in Ireland would know that the daylight and sunlight impact in apartment developments has actually been subject to judicial reviews. So it kind of goes a step above the planning process, and it's been the sole reason why multi-million euro developments don't get planning permission. So the types of advice we'd be giving after analysis would be to things like stagger the balconies to living spaces to improve access to daylight. We'd be looking at the working plane, you know, the height of the window sill relative to the floor. We'd be looking at trying to get dual aspect where possible, but I suppose it's just the point more that the daylight analysis for planning has become so critical, and hence the analysis we carry out as part of that to inform the design team, and the digital tools we use are extremely important. Daylight is obviously also very important for health and well-being of employees, and it's regularly tested for the likes of the BREEAM LEED or WELL building standard. So in BDP, we would, you know, regularly produce analysis and reports for these sustainability assessments to bank credits and to achieve certain ratings, whether it's a BREEAM Excellent, Outstanding, or a LEED Platinum Gold or WELL Gold. You know, the circadian rhythm of natural light to the human body and the influence of it is kind of well researched, and there's lots of data out there. The WELL Building Standard, for example, states that on average, office workers who have good access to daylight and are close to windows get 46 minutes more sleep on night on average than someone who doesn't. So I suppose that's looking at the daylight analysis, but then we also need to consider the facade analysis and the building form and the impact on energy. So if you take Bonham Quay in Galway, which is 4 office blocks that we're working on, we've two of them built and one to the third starting this month. So BDP back at planning stage and during kind of scheme design would have used IES virtual environment to model the building's form and test various glazing arrangements, glazing ratios, orientations, and the use of solar control glazing to find the balance between reduced solar gain in summer, free heating in winter, but also maintaining good views out to the harbour and daylight to the spaces. So in bottom key on the right, for example, this modelling informed the glazing ratios and vertical fins for the solar shading. So like from the model itself, kind of took a few snapshots, but the intent when we looked at this was to look at, you know, how in the morning during winter we can get that direct sunlight and solar gain into the office to preheat the office when heat losses are greater, but then in summer keep that afternoon sun shaded and its impact for cooling loads down. The Esp Headquarters in Dublin was another very large project that BDP were involved in, that we carried out very extensive solar and daylight studies for, going back about 10 years now. So this project has been complete and open for the last 9 months. So you can see the models on the left there, but essentially we designed glazing that adapts to fit its environment. So, you know, I suppose it's hard to tell on that model there and due to the scale, but the glazed areas change with height to even out the daylight and solar gain. So on the lower floors where there's more shadow from existing buildings and we want kind of more daylight and we're not as concerned about solar gain, we have larger glazing ratios, and as the building goes up the floors, the glazing ratios shrink and shrink and shrink, trying to get that optimization between daylight and reducing solar gain. We've also kind of specified and steered the design team in the direction of certain solar control glazing to encourage solar gains from the north and east in the morning, and then to shade the glazing on the west and south where possible. And this reduces the asymmetric radiation across the floor plate. So to give you like a very specific example on this project, where we looked at solar selective shading fins. These are fixed fins, you know, part of the facade. They don't move. But what we did when we were carrying out the analysis was look at how we can provide opening sections for the windows to allow natural ventilation, fixed sections that, you know, will have blinds associated with them and for visual, but also to utilize the vertical fin and the glazing position to block to allow the morning sun to preheat the building, but then to block that afternoon sun. So you can kind of see on the image to the right there, we have in the morning essentially where when the sun rises, it does allow penetration into the office to get that useful solar gain. But in the afternoon in offices when cooling loads are high, temperatures outside tend to be higher, what the fins do is they actually shade that particular window. The Ren Hotel is another project we carried out in Dublin that has been open since September last year, and we did something very special with the west facade, which I'll go into a bit more detail on. I suppose to put some context on it, the hotel is located, if anyone knows Dublin, it's right in the heart of Dublin. So Trinity College is there on your right. Grafton Street is kind of the main shopping street in Dublin. So it's only a short walk to, I suppose, the busiest. It's right in the city centre. And this has obvious constraints. It opened to guests in September 2021, has 137 hotel rooms on a lower ground floor bar and restaurant. When we looked at analyzing this, I suppose on the previous image, you could see that there was quite an extensive glazing on the west facade, which kind of was for multiple reasons, both kind of from an architectural aspiration perspective, but also to kind of sell the building from Exchequer Street, which I'll explain later. But we were conscious that too much glass obviously increases energy use, and so when we looked at the form factor and glazing ratio, we did optimize where possible. So, you know, the north facade and the south facade have actually no glazing whatsoever, and the east facade is kind of punch windows, so a lot more reduced and refined. We did kind of have a lot more square or rectangular building initially a planning grant, but the fire cert required us to step back from existing buildings of conservation nature, so there ended up being a little bit of a step in the facade. So with the west facade, as I talked about, where we did something a little bit different, a folded facade was designed using curtain walling into the elevation. So the view on the right is just a CGI from Exchequer Street, which is basically this lane used to be a bit of a rat run for taxis just to kind of go down and turn around. So the intent was to try and draw people's eye down to the street who are walking by Exchequer Street, which is a very busy shopping street that leads right down to Grafton Street. So when we looked at kind of different analysis, obviously like the most straightforward approach for a facade is just a straight flat facade, but we looked at different options for the facade and how we could kind of create something unique. So when we were analyzing this, I suppose what we do know is that in Ireland, the sun rises in the east and sets in the west. So in the afternoon, this is being a west facing elevation, we knew that there's going to be a lot of solar gain, and we wanted to reduce this on the west facade, but equally not compromise on the room quality, daylight, views out to the city and the architectural design aspiration. And this was a BDP multidiscipline project, so we had BDP architects, civil structural, and M&E involved. And so ultimately we ended up creating different orientations with that curtain walling. So this kind of view gives you a good sense of it's subtle in nature, but I suppose if you think about the summer, in the summertime, in the early afternoon, you have the sun hitting, those panes of glass that are facing that kind of southwest orientation, and then in the late evening, you have the sun hitting the northwest elevation. So each of those panes of glass, there might be a bedroom behind two of them. So what this strategy ultimately did was it reduced the peak cooling load across the entire facade by about 45%, so that at any given time, only 50 to 55% of the west facade was actually getting direct solar gain, whilst the rest of the facade was slightly in shade, which just kind of helped reduce cooling loads, which means smaller plant and lower energy bills. But back to the Esp Headquarters, another good example of where we use IES virtual environment and the macro flow application for testing our natural ventilation in a hybrid ventilation office design. So I suppose for those that don't, hybrid ventilation is kind of what we would coin as the third generation of low energy office, in that like there was kind of natural ventilation was seen as the sustainable approach, and then lots of companies were still looking for air conditioning, so the mixed mode approach was kind of the second generation, where you had openable windows and a HVAC system. Hybrid ventilation is kind of the third generation, because what this system does is it kind of links all three, whether it's heat recovery, natural ventilation, but in a controlled manner that means they're not fighting with each other. So the advantages of this are there's extremely low energy use, it's excellent thermal comfort, air quality, still gives user control and occupant control. There's no constraints on the room locations and plan depths. So with naturally ventilated offices, you need to keep the plan depths quite narrow, so you can get that cross ventilation or natural ventilation to the spaces, whereas that doesn't work with every site and client brief. And there's far less openings and motors than in a mixed mode system. The components within a hybrid ventilation office include air conditioning systems, heat recovery ventilation, activated openings, manual openings. There's an allowance for night cooling, and there's very innovative control routines which are essential for this type of system to work. So kind of what we look at it is like the hybrid palette, and ultimately is taking the best of all systems for better health, energy, comfort, and air quality. So to kind of get into the minute detail on just one particular aspect of this design, if you look at the windows and how we use macro flow, we ended up designing windows that had, I suppose, two different sections. We had vision panels, which were solid, not openable, and then we had openable sections which were not translucent, so they were opaque. And the reason for this is that we found with research we've done on previous office projects we completed is that, whilst you provide openable, naturally ventilated spaces, depending on their orientation, and even just by occupant use, not opening the blinds when the sun goes away, people were just closing the blinds, and this was impacting on the natural ventilation strategy. So by doing this, it meant that a user could adjust and change the blind height as required, but it wouldn't affect the natural ventilation strategy. So at high level, what we have is motorized louvers with user override. So there's switches on the wall that a user can open or close them if they wish to. I suppose high level means there's less drafts, so these can be open more often. It's less likely during kind of that medium temperature that they're going to close them. It allows for secure night cooling, so it means that you don't have a large openable section that's open in the middle of the night for a security perspective, but you can open it if conditions are favorable and you want to get that free night cooling to cool down your building and your slabs. It allows for a pre-occupation purge, so at 7 a.m. you kind of just like get the air quality very strong naturally without having to turn on all the air handling units. And there's also a nice little feature with trickle vent to reduce cooling load. So essentially on weekends and things when we're not occupied, depending on the conditions, those louvers at the high level can just crack open a small bit. And what it does is we've got a really airtight building that get very airtight, but then in summer months when you want to keep that background ventilation moving, you're able to just kind of kill that air permeability and allow a lot more of it. At lower level then we have manual windows which give those occupants a sense of control. Something again from post-occupancy surveys, we found that if you automate everything and take that control away from occupants, it's something that they tend not to like and kind of push back against. And as I said before, the solid vents avoid blinds over open windows. In terms of mechanical integration, we have mechanical systems that automatically respond. So it's based on measuring space conditions. So essentially, if the carbon dioxide levels or the temperature in the space, are favorable for natural ventilation, it will cut the air conditioning to that particular space, and it results in, I suppose, it's a complex BMS and building management system, but there is no conflict between the systems. So the general strategy, and it's all user adjustable, is that if the temperature is above 12 degrees, the building management system will open the windows if the occupants don't. If it's between kind of 6 to 12 degrees, the occupants can open the windows. And if they don't, and the CO2 levels start going up, the heat recovery ventilation will kick in. And then below kind of 6 degrees, the heat recovery will operate and the occupants will be discouraged from opening windows. So there's a little delay on it. And basically it just means that like it kind of maintains the fabric resilience and the design that we went to good lengths to try and achieve during colder weather. So I suppose one thing that's important to note and why this system really works is that in sealed offices where you don't have open windows, where there's been such a push over the last 10, 15 years to keeping continuously increasing insulation. And it's actually gotten to the balance where, if you keep increasing insulation in certain building types, like offices, for example, the insulation and air leakage and the tightness actually increases the energy use, because offices in their nature are cooling. So they, for 80% of the year, they're actually in cooling mode just with the number of occupants, PC desktops, comms room, etc. So in a hybrid solution, the fabric over performance in warm weather is handled by just adjusting that ventilation. So again, in nighttime cold weather, the vents closed are kept closed and the fabric performance is maximized. In nighttime warm weather, those motorized windows open for night cooling. In the daytime, when there's a net cooling load, those motorized windows are just in trickle mode and the occupants then can open the manual windows as they wish. And in warm weather during the day, the motorized windows are automatically opened by the BMS. So in terms of utilizing thermal mass, again, these two images come from the Esp Headquarters. In BDP, we kind of believe that both from a kind of materiality and reducing the extent of materials, you should always look at exposing thermal mass, but equally from kind of night cooling, reducing peak loads, there's lots of benefits. And I suppose the point we always try to make to architects is that exposed concrete doesn't always require exposed services. Sometimes we have clients who come and say they don't like their exposed services look, and we say that's fine, there's ways around it, and there's kind of two examples in front of you of how we do that. Equally in the Ren Hotel bedrooms, so we obviously have, when you walk into the lobby, you've got lots of services above the ceiling which are in the bulkhead for the ensuite and the initial bedroom entrance. But then as you step into the bedroom, it's actually an exposed concrete slab. And what this does is that this exposed slab absorbs that solar gain that we couldn't get rid of through the facade during the day, and then it releases that heat at night when inevitably we're going to have higher heat losses, particularly in the Irish climate. Again, this is just one more example of the UCL Student Services Centre, which was completed in 2019. This features exposed thermal mass. You can see that it's very neat. It doesn't have to be all kind of exposed services with running ductwork. Again, this was a hybrid ventilation project, and it also had a re-injection open source ground loop for cooling. In terms of embodied carbon analysis, BDP throughout our practice utilized one-click LCA for embodied carbon. It's something that I suppose there were probably it was only every couple of there's very few projects maybe up until 3 years ago, and I suppose like the rest of the industry, it's kind of exploded and now is becoming the norm. I won't go into too much detail on this, as I'm sure it's been covered already, but I suppose the one-click LCA software, it's cloud-based, it's got a very large database of materials and EPDs. It's LCF, specific products and general materials and constructions. It has a very user-friendly interface and has a Revit plugin and ability to run options and pick alternative elements, which is where I suppose it comes to strength for us. You know, data would show that a typical new build office may range from 600 to 1200 kilograms of CO2 equivalent per meter squared. And what we're finding now is, and a recent client has asked for, is they're looking for 350 kilograms of CO2 for office buildings and 300 for apartments to kind of align with the LETI target. And so this brief is starting to become the norm. This is what we're finding, and it can be very challenging. Particularly, we're finding in Ireland. I know our counterparts in Europe and probably throughout the else in the world maybe don't have the same challenges with the fire officers, but in Ireland, the current fire regulations are very restrictive, and so that's limiting our allowance to use structural timber. So we're still kind of in the dark ages of having to use steel and concrete for structure, which makes up, you know, a large proportion of the embodied carbon. So those targets are very, very difficult to achieve in Ireland. This is the kind of type of graph we would end up producing as part of an LCA report. What we'd start with within our embodied carbon analysis is a kind of baseline project, as everyone would, and then we'd start introducing optimization. So this particular one was a residential apartment development. We had a baseline where we started looking at, you know, timber stud partitions, composite windows, different insulation types, plasterboard types, even down to like, you know, we obviously introducing KGBS into the concrete, but, you know, you get down to the point of having to look at flooring and ceiling finishes just to get to that level. What we actually have now in BDP as of January as well is we've introduced a new QA process. So regardless of whether it's part of the client's brief or sustainability brief or not, we're required to follow these activities across the REBA plan of works. So at stage one, we have to carry out site context analysis and review post-occupancy evaluation feedback from other similar project types. Then in stage one, we've got the sustainability brief and target setting, and we have to identify a sustainability champion within BDP who I suppose is separate to the design team. Stages 2, 3, and 4, we need to carry out sustainability charrettes, a whole life carbon analysis on all of our buildings. We need to look at a materiality strategy, assess the climate change risk assessment, so things like TM59 analysis. We have to carry out environmental assessment of some sort, even if it's not targeted, and, you know, or I suppose chase just the design intent if you looked at, and we need to look at the green infrastructure strategy. Stage 5, we review materiality again. Stage 6, you know, further work on the environmental assessment, and at stage 7, we are, I suppose, trying where clients let us to carry out post-occupancy evaluations. So at each stage, we're required to complete our new environmental performance review, and that has to be formally submitted, which ends up in a central database that the full, I suppose, BDP sustainability team can look at, meaning that, you know, as it's only started in January, the data is only coming in, but say in 5 years' time, we'll have a very large database across the world with multiple projects involved. So with active design, the Ren Hotel is one where I kind of wanted to talk a little bit about the innovative HVAC design within this project. So this particular hotel is Ireland's first net zero carbon operational hotel. It has no fossil fuels, no local pollution. It's BE or A3 rated, and that actually is one of only a handful of hotels in Ireland. Its monitored energy use is currently tracking 4 times better than good practice. It has an OREOR, which is 4 times the NZEM requirement, and has very low water use. So it's about 160 litres per bedroom versus 1,050 litres, which I'll talk about later. And the monitoring of that is still ongoing. So, you know, at my desktop right here, I have access to the BMS remotely, where I can get on and have a look at all the different meters. It's already, even though it's only been open for 9 months, has won a number of awards, including the Sustainability Award at the Building and Architecture of the Year Awards, the Leisure of Tourism Award at the Irish Construction Excellence Awards, and the Building of the Year and Sustainability Award at the GGB Awards. And we're shortlisted for a few more. So with this, I suppose I already talked about this folded facade on the west. So what we looked at with our HVAC design was how do bedrooms on the west. I suppose what we found is with our modeling was that the bedrooms on the west in winter were still needing to be cooled, because, you know, people were going to be opening the blinds, looking at the views, and, you know, there's going to be direct sunlight on that facade. So we explored how the system could transfer this energy to the rooms in the shadow on the east facade, or to the hot water when it wasn't needed. So kind of in plan view, you see your bedrooms on the west, you know, they're in cooling mode even in winter, or they're in cooling mode even in winter, but on the east facade there's heat loss because they're in shade. So what we use is a air source heat pump and kind of complex system to transfer that heat across. So what we ended up with, and this is very a kind of simple diagram, but we essentially had air source heat pumps, so 4-pipe chillers, which provided cooling and heating to the hotel bedrooms. We had to provide heating to our heating coil within the fresh air AHU. It had a full heat recovery thermal wheel. And then I suppose when that heat wasn't being utilized, what we did is we introduced an additional water to water heat pump, which essentially boosted the temperature from 45 degrees up to 65 degrees, which was being used for hot water for showers and wash hand basins, which I suppose the engineers on the call would know that for Legionella risk, you need to store your water at that temperature. Other considerations with this type of system, so traditionally hotels around Europe at least are VRF refrigerant type systems. The challenge you have with these systems is, for one, they're quite noisy. So on the image on the left is actually taken directly from a very popular VRF system, and essentially they're saying themselves they're branch selector units, so they're individual units on every floor that run multiple fan coil units. They need to be at least 5 meters away from sleeping accommodation. And as you can see in the image in the middle, the width of our hotel is only 14 meters. So finding a location for that proved very difficult. Also, the refrigerant type systems have, I suppose, not only are they high in embodied carbon, they also are much more aggressive when it comes to heating and cooling. So their supply temperature is typically 40 degrees in heating and 11 degrees in cooling. So with the water-based system that we designed in the Ren, we got rid of those acoustic concerns because all the pumping is back at the plant room on the roof, and it's a much more comfortable way of supplying heat at 29 degrees in heating and 13 degrees in cooling. And as I said, low refrigerant use also means lower embodied carbon. Within the kitchen, there's a full commercial cooking kitchen within this project as well, full restaurant with 40 covers. And with the kitchen consultants, we managed to convince them to design out fossil fuels using induction hobs and all electric equipment. So the result was, a building which is quite unique, a hotel building which is quite unique in that there was no gas connection, no boiler room, no flues, and zero pollution. The other benefit to the operator was there was a single energy bill. So I suppose, I'm not sure what it's like in other countries, but in this country, and it's only getting worse, like the service charges, standing charges, VAT, PSO levies, they actually end up making up about 50% of the bill. So before you've even used a single kilowatt of electricity or megajoule of gas, you are paying a certain standing charge or service charge just to be connected to the grid. So what by removing fossil fuels altogether from the project, we just removed an entire bill and kept those standing charges lower. In terms of carbon energy generation in Ireland and the carbon intensity, it varies obviously country to country whether heat pumps stack up. In Ireland, the carbon intensity has halved in the last 15 years, and coal is set to be removed by 2025, with peat being phased out as well. Look, the government have plans to have 70% renewable energy by 2030. But I suppose the key point with this is that, like, as of right now, using electric heat pumps is, that due to their efficiencies, it's about a 50% improvement on the air source heat pumps for heating than using a gas boiler today, and domestic hot water is probably on par. But the use of electric heat pumps gives certainty of carbon improvements, because as the national grid reduces over time and decarbonizes, so will the carbon impact of the hotel. Obviously, this is very complex design coordination. It takes time, but the dedication is worth it to be innovative. So I suppose that kind of leads me nicely on to BIM and our use of it on most of our projects. So across the majority of our projects, we utilize BIM to level 2. Revit is the most commonly used software, and our Revit team utilize multiple plugin applications to improve efficiency. So this project is the MISA Mercer's Institute of Successful Aging in St. James's Hospital in Dublin. And that's been open about 4 or 5 years. I suppose I threw this image in because, as everyone knows, I suppose I could spend an entire presentation talking about BIM, but the reality is, like, the coordination capabilities of it are quite extensive. So this is just a screenshot from the facade taken away from the BIM model in Esp Headquarters, and the coordination that goes into it and the time and effort is spent at design stage. It really pays off kind of during the construction stage when it's being built. So one of the tools we use to try and be more efficient with Revit is the Dynamo, which is a visual programming language. So it's used across the AEC industry for various use cases. And what it does is it helps users process and access the rich BIM data. It's an information management tool, a geometry tool, and ultimately what it does is it automates repetitive tasks, which save time. So BIM's data can be validated easier and with more confidence, and it gives solutions to real world problems that can be achieved quicker using computations. So again, I could spend an entire presentation talking about this, but just as an example, obviously, whether it's architects or engineers, you're going to have multiple drawings, particularly of a building that's complex, different services, different floors. And what Dynamo can do is, from Excel schedules, it can create levels, views, and sheets. Just kind of, one click. And once you put that time in at early stages, you can then roll it out for every project. Dilux then is used for lighting design as a comprehensive planning tool that provides the necessary functions for professional lighting. The software calculates and visualizes lighting for indoor and outdoor areas and the entire buildings and individual rooms to parking spaces and road lighting for planning compliance. I think I'm running out of time, so I'm going to speed up. The Pro design is used for cable sizing. So formerly known as Amtech, we use this software to design cable sizing for electrical distribution and networks. The software sums the loads and calculates the required cable or busbar capacity for each circuit. And it also carries out voltage drop calculations to assist in complying with BS 7671. As I said earlier, we do utilize CFD analysis in very specific applications. We wouldn't use it across an entire project, but if we're looking at one particular design, take for example this music performance hall in a third level college we worked on. The intent was to serve this by a displacement ventilation system, which basically is supplying air at low level and exhausting it at high level. So we modeled this space using microflow in IES to ensure that things like the high output lighting for stage lighting and performance lighting doesn't create overheating issues, and that the occupants are kept comfortable. So I suppose in terms of our design hierarchy, we've looked at passive and active design. So now moving on to renewables and monitoring. So we have projects that are intended to be 100% run by on-site renewables here in BDP in our Dublin office, and we're currently working on, for example, this is one I can talk about. It's a little store that will deliver the first truly zero carbon store in Ireland. It's going to be 100% on-site generation from solar photovoltaics that even offsets the electric vehicle charging requirement. But what this project has that many don't is that it has a roof to floor area ratio of 1:1. So I suppose that is obviously not always practical. In multi-story city centre buildings like the Ren Hotel, which I've shown sections here for, it's a lot more challenging. So with the Ren, we have 32 metre long, 14 metre wide and 9-storey above basement project. So your solar panel potential is very limited with a ratio of only 1:9. And in fact, the World Green Building Council themselves recognise that in most situations, net zero energy buildings are not feasible. And this is exactly right now with the technology we have, the type of constraint that we're actually finding within the industry. And anyone who's actually worked on delivered projects, complex hotel projects, office projects, commercial projects, they know that the reality is actually even more challenging for solar photovoltaics, because what's not accounted for in your kind of initial concept drawings and sketches and designs is that roof area ends up being taken up with fall arrest systems, green roofs, plant, AOVs, smoke extract. Before you know it, if you take the Ren Hotel, we've virtually had no space left for photovoltaics, so we had to look at different approaches. So to increase the solar photovoltaic potential, it's important to think outside the box. So where possible, we looked at things like the top image on the left is a secondary school in Ballina here in Ireland, which we, I suppose, had photovoltaics on the roof, but introduced further and more of them using covered walkways for the students. Equally, the office project there in Dublin on the right, the design was to have open atriums, outdoor atriums that had coverings using the photovoltaics. We got 1,000 meters squared on that particular site with those 3 offices, and the canopy the array is also used for rainwater collection. So other renewable energies and options that are not typically practical are things like wind, which is not feasible in most locations for obvious reasons: planning, noise, turbulence created by other buildings, the structural requirements needed, and the increased embodied carbon associated with that. Biomass, look, it is a low fuel, but it's the space for fuel, deliveries of fuel, local pollution in the city centre environment, the air quality is impacted, not really practical. Combined heat and power, it's an option that some hotels and some projects are looking at. Personally, in BDP, we tend to steer away from it. It still burns fossil fuels, so there's a reliance there. It creates local pollution, which impacts the air quality, and the building will always require carbon offsets. So even when the grid is decarbonised, you'll still need carbon offsets because you're burning fossil fuels. Solar thermal, instead of photovoltaics is an option. It does generate hot water for free, but it needs a much larger area. It's expensive now relative to photovoltaics, which have come down in price, and the Legionella risk needs to be designed out. So in several BDP projects, we're utilizing air source and water-to-water heat pumps and waste heat and recovered heat through heat that's normally rejected when cooling, and heat recovery on the air handling unit. So just very quickly, I suppose for those on the call who don't, I suppose have heard of heat pumps, but maybe want a simple explanation. If you think of your fridge at home, your fridge has evaporator coils which are keeping the contents of your fridge cool. And at the back you have condenser coils and a compressor which is giving off heat. So it's counterintuitive, but leaving the fridge door open will actually heat your kitchen, not cool it down. So I suppose the way a heat pump works is that there's 2 circuits with 5 different operating modes. In cooling mode, it's exactly like your fridge at home in that it's rejecting heat to atmosphere, but it's using the cooling to cool the building. In heating only mode, it's the exact reverse of that, so that the heat is going to the building and cold air is being rejected to the atmosphere. And in heating and cooling mode, that's when there's simultaneous heating and cooling, and this is where these units really come into their own and are very efficient with COPs of up to 8 or over. So what that means is that for every 1 kilowatt hour of electricity in, you get 8 kilowatts out. There's 2 other modes there, which are self-explanatory. Further technologies then can be added to reduce the energy. So the Esp Headquarters we touched on earlier, for example, this heats for free while cooling, but when there isn't a cooling load in the building, so say at nighttime, for example, the phase change material is actually used in the Esp Headquarters, but in another project of ours, the National Gallery, we used ice banks. So what this does is that it can reduce your total plant because it reduces peak cooling loads. So you're cooling at night, generating all this cooling medium and releasing it during the day when you need it. So it increases that free cooling. Another thing to consider, and one benefit of these heat pumps that capture heat and reuse it, is that chillers create the urban island effect. So if you've ever been in New York, shown here, but any big city, you'll know that during summer months within the city is a lot warmer than it is outside the city. The reason for that is that all the buildings, whether offices or restaurants or hotels, are air conditioning their buildings inside, and they're dumping all this heat onto the street, which is just increasing the temperature locally. So the air conditioning units have to work even harder and end up throwing more heat out. So it's just a constant cycle. And so why not utilize that heat? In terms of BMS monitoring then, so after a building has been handed over, BDP like to get access to the BMS and monitor the building over its first 2 years of operation. So we typically review and monitor the sub-metered energy use, air quality, water use, and we interrogate trends both daily, weekly, and seasonal, and try to find system inefficiencies. After the first year, we typically make recommendations for improvements, and we use that data gathered to inform the next generation of design. Unfortunately, we don't get access to all our buildings, but just to give you an insight into some that we do have. So the Esp Headquarters been open about seven months now. Initial monitoring results are showing that we have almost zero heating energy. So it's 7 kilowatt hours per meter squared a year it's tracking at, and almost all of it's from recovered heat. We have almost zero cooling energy. So this is the one with the hybrid ventilation. We have no active cooling at all in the open plan offices until it goes over 20 degrees outside, which in Ireland is a fairly rare occurrence. 30% of that cooling then is free cooling from the ground. We have ground loops within this project as well. And overall, the energy is tracking about 30% of what a typical green office would be. So I suppose to put that number into context, we're currently tracking an operation energy for heating, cooling, ventilation, auxiliary at about 20 kilowatts hours per meter squared. So if you take the Ren Hotel, this is like a typical trend graph that I'll get for 2-week period, showing the dates on the left and hours of the day on the right. So that usage trend, the peak energy use for this particular hotel is actually occurring at 4 a.m. and that's actually, funnily enough, during the Legionella cycle for hot water. So heating the hot water up to above 65 degrees once a day to kill any Legionella risk. In terms of water use then, we're seeing our peak water use is occurring between 8 a.m. and 10 a.m., which is as you would expect, people kind of waking up and having a shower. And so what we're, one of the advices we gave very early on is, okay, well, this 4 a.m. Legionella cycle, like let's push that forward and get that closer to the peak use so that your hot water is not standing there stored for longer periods of time when you have to run that cycle anyway. Now, in terms of room control then on the BMS system, within the Ren Hotel as an example, we utilized a very advanced room control system called VDA. So this does the obvious thing that most hotel rooms do and turns off non-essential room loads when no one's there, but it has other features like automatic control of blinds to reduce solar gain in the west facade. So it has an added wake up function as well, which is very nice, I think, in that guests, instead of asking for a phone call to be woken up, can be woken up by their blinds automatically opening at say 8 a.m. to sunlight. It setbacks the room temperature during unoccupied hours and overnight. All the limits on the user control can be adjusted, has lighting scene selection to reduce lighting energy. And the system knows who's in the room and for how long. So this is great for the operator, for the management of housekeeping. And even like a nice little feature is the room preferences can be adjusted. So if you have a guest from America, for example, you can change a check-in to be degrees Fahrenheit. Reducing plastic waste from a sustainability perspective is another strategy we implemented here. So we provided free chilled water for guests on every floor, little chiller in the corridor. We also provided fresh water to the wash hand basins, which is quite unique in hotel projects. So when I say fresh water, is direct water from the mains, so similar to kitchen sink at home. So I suppose why this is often overlooked is due to the concern that the mains water supply will drop off for a short period and all of a sudden your sinks don't work. So we just did a simple little measure and designed in some redundancy. We essentially have a normally closed lever valve, which loops back to your cold water storage tank, which is 24-hour storage, 25,000 litres. And in the event of the public mains dropping and that mains water dropping out, there's basically two valves, or one's closed, one's opened, and all of a sudden the cold water storage tank is providing the cold water to the washing basins. Simple but very effective. And just to leave you with one last thing, and this is my last slide, to think about and kind of food for thought. With the Ren Hotel, this is a great example of that. It's not always, we talked about the heat pumps, we talked about the facade, passive design, building form, the highly efficient HVAC system, but it's not always them that saves the most energy. Sometimes it's as simple as specifying the right shower head. So we spent a lot of time with the operator, with the architect, interior architect, looking at a shower head. They wanted a rain shower. A typical rain shower is 25 litres per minute. And we were saying to them, that's going to, one, use a lot of water, but equally the hot water use is going to be huge, which is a big driver for hotels for obvious reasons. So in the end, we found a shower head after testing multiple restrictors on different shower heads. We found one that everyone was happy with, got it down to 8 litres per minute. And the Ren Hotel is currently tracking at 160 litres of water per day versus guidance, which recommends 1,050 litres of storage per room. At least that's guidance from Dublin City Council. So what this ultimately reflected in is reduced cold water storage requirements for the hotel and space taken up by tanks. It reduced the hot water generation bills by over 60%. And we're also still monitoring the system to highlight inefficiencies and leaks. So thank you for your time and happy to take any questions.
Okay, thank you very much, Patrick, for your very insightful presentation. And so just to quickly move on to the question and answer session. Thank you both for very informative sessions. Just to mention from Andrea, it was really interesting to see some of the frameworks and standards already in place that are supporting EPDs, and even guides that go as far as also give data on the expected lifespan of the different MEP components. That was very interesting to learn about. Patrick, I particularly found the design hierarchy that you had given, especially from the passive design, is what piqued my interest. And it goes to show also how simple strategies within that tier alone could help projects get to green building status, also from the planning phase itself. So there are questions that have been sent in, and the first question, which goes to both Andrea and Patrick, is: do you think natural ventilation is a feasible option to reduce operational carbon emissions and embodied carbon? It would be cheaper to build, to maintain, and to run, in particular in hot climates like Kenya. And the second question also still goes to both of you, is fully glazed buildings have become the norm for office buildings around the world, regardless of the local climate conditions. What are your thoughts about that from an MEP point of view?
Will I go first, or do you want to? I can answer first if you want. So,
Okay.
yeah, so I suppose in my experience, like having worked in Ireland, has the climate for natural ventilation, and it's a no-brainer to use it where possible. What you find though is that with office projects, for example, the tenants that were coming in, particularly in Ireland, we have a lot of kind of headquarters, whether they're Twitter, Facebook, So they, being American companies, they want air conditioning, they want fan coil units. And so this is where you need to look into this kind of hybrid mode and mixed mode, but it doesn't mean you have to seal your buildings up, particularly where external conditions are kind of useful. It's worth opening your buildings up where possible. In terms of reducing embodied carbon, what I found in my personal experience, we do have naturally ventilated buildings we've completed only, but in my personal experience, is the new buildings, office buildings designed today, they're still looking for HVAC systems. So in the end, you don't kind of reduce you still have the ductwork, you still have the chillers, the heat pumps, so your embodied carbon doesn't necessarily get reduced. Just to touch on, depending on the country, have experience working in Australia, designing buildings in Perth, it does prove a lot more difficult because you have a lot less periods of the year where natural ventilation is feasible.
And following up on that, yes, I also agree that depending on the location, not only the location, but and the weather, but also the conditions around the building have many implications onto what we can actually do with the design. So you may find that it could be used throughout the entire natural ventilation for the entire year. That will depend on the type of building, the size of the building, and if not, a hybrid solution will always be helpful. Yeah, as it has been mentioned, the usage of that natural ventilation may not be for a large part of the year, but we could, through different methods of analysis and identifying the requirements for the building, we could make it as long as possible. One of the things that have been touched on today is that the passive measures to make sure that the least amount of solar gain is introduced into the building, and also the controls that can be provided to the building in order to ensure that it's also well used, because sometimes we do give the user the opportunity to open the windows, but then it doesn't happen. So it's also about giving a control strategy that will help them, that will guide them, and that it will be easy to maintain, because they could make a large impact onto that operational and embodied carbon throughout the year. And following up on the next question that you have asked about the fully glazed buildings, that's something that yeah, as we have discussed before, is not only requested in Kenya, but also requested throughout in different places of the world. But it's about identifying if it's actually in the right location. So for example, as you said, software as IES and calculating the radiance on the solar gain to the building can be very useful to define if we do need that amount of solar gain on specific floors or in specific facades. For example, we may have a larger amount on the north side than on the south in the UK, or it could be different depending on the country where you are. But also measures to limit, even if it is a glazed facade, to limit the solar gain through different measures, either outside of the glazing or within the glazing, to um, improve how much cooling loads is required to the building, and with that the operational and the embodied carbon.
Yeah, and I suppose just to add to that, I suppose from at least a personal experience in Ireland, I think regulation, building regulations does go a long way to I suppose challenging that concept of just fully glazed buildings. If you take the building regulations here in Ireland, we have to carry out a Part L compliance check. So basically benchmark our actual design versus a reference or notional building. And if you end up having to put it into context, for an office building, for example, the reference building in Ireland only has 40% glazing ratio. So if your actual design has a glazing ratio of 80%, then you're on the back foot straight away, and you're like, all the measures you're implementing, like improved lighting controls, lower lighting energy use, all these advanced HVAC systems, all you're doing is trying to make up that ground. So as a starting point, it really does help the likes of myself, who's an M&E engineer, from day one, say, look guys, we're trying to meet the minimum building regulations here, And to do so, you can't have 80% glazing ratio. So obviously it varies country to country, but I think like in my experience, having worked both in Australia and Ireland, you know, regulation ultimately is the best stick. It's better than a carrot, really, for a lot of clients who push their own agenda.
Thanks, Patrick and Andrea. I hope those responses answer the questions that have been asked. So just to go to the final question from this session is for still both Andrea and Patrick. What are your thoughts on the virtual environment, that is the metaverse, to stimulate lighting and the type of materials? It would not help understand ventilation, but would it help with understanding how occupants react to a building interior?
Yes, so I'm understanding that you're mentioning about simulating the lighting for building, and that's something that we do in general. We definitely think that having good natural daylight on each floor will identify how much lighting is required, and with that, it will actually impact on the ventilation, because you may need more cooling load for the space because of that amount of heating provided by the lighting. And we also do provide information about the materials. Now, it may be more related to the facade in that case, in terms of how do we absorb the heat, or how do we, let's say, re- reject the heat at night so that it can be used for other things. So both lighting and materials are included within the design, and the intention is that yes, they will help because they can give us an idea of the load throughout the year, and also the requirements in terms of the controls that we may need to implement.
Yeah, I suppose from my perspective, yeah, I definitely think there's room for it, and it's something that will become more and more useful. Like I suppose, like I can even, I suppose when I saw that question, the first thing that came to mind is, you know, how we have used, you know, the virtual environment, I suppose, maybe at not the lesser extent to what it is capable of doing it so, but we've used it to kind of demonstrate and convince, you know, whether it's clients or architects to proceed with certain versions. So if you actually take that Bonham Key example I had of the vertical fins, when I actually showed in a presentation a few different images of the solar gain and how the sun is impacted in the morning and the afternoon to the client, they were actually more interested in the play of light and how it affected light across the facade, and they liked the fact that it introduced all these different, you know, it wasn't just a blanket of solar gain, and that's actually what convinced them to utilize vertical fins as opposed to the energy savings associated with it. They just like the fact that it created kind of a play of light on the floor. So like it's, I think inevitably, you know, as you know, where technology is there and as kind of users get more familiar with it and up to speed on things like that and skilled up, that will be very useful for like simulating lighting, solar gain, daylight, all that stuff. Yeah.
Wow, interesting to hear. There's one final question that has just come up. What recommendation for emerging economies that require a large number of new buildings? This goes to both Andrea and Patrick. Okay.
I can jump in there. There are many. I think learning from the past will be the best, because obviously there has been various projects or software tools that have already been used for uh, cities at the moment, and understanding how they can guide the solution in the future. Not only that, is about connecting different areas, and if we were going to design many buildings, they can be integrated in a way, they can be supporting each other, they can share load, they can be more interactive, and that will definitely have a complete different output, as if we were having to construct each building at a time. So yeah, understanding for things from webinars like this one.
Yeah, I suppose like my recommendation, and you know, at the risk of it being quite a sweeping statement, because obviously every local area has its own challenges, but you know, I suppose there's been a bit of a, I suppose, a step forward, I would say, in Europe and maybe the States recently, in Australia, for moving away from fossil fuels. And I think with emerging economies, I suppose don't make the mistakes of the past. The technology exists now today to step away from that. There are buildings that are 100%, like I've shown you. We've got a couple here in Ireland that are 100% electricity. And so I think going backwards and starting to introduce fossil fuels, if you're creating a large number of new buildings in a certain area, is just the wrong way to go. And if you are going to do that, as Andrea kind of noted, like district heating or district, sharing, if you have retail loads that is offsetting heat for hot water, using an apartment building, there are ways to reduce energy and be more connected. So that would be my kind of main recommendation, is like look ahead at what in 10 years the technology is going to be significantly better than where we are now. So think about what the future expectation is, not what we're looking for today. And I suppose I should say that, whilst you might not always get government support for that or building regulation support for that, it's platforms like this, communities like the Share Your Green Design community that, I suppose give the insight and worldwide and kind of show what has been done elsewhere. And that can then be kind of communicated and shared with future clients, and, hopefully you can convince them to do it.
Great. So now, thank you for the questions, and hopefully from the responses that you've been given, it gives you insight, and also that you've learned that of the different strategies and the in-depth analysis that goes into informing decisions in the planning phase of both projects. So I'd like to quickly get to the convenience break. As opposed to the 10-minute break that I previously mentioned before, we'll have a 5-minute break. Drink your water, stretch your legs, and we'll resume the second part of the session in 5 minutes.
Thank you.
Thank you.
Okay, welcome back to the second part of the session on Whole Life Carbon Part 2, and also the final session on the series on tools for green buildings webinars. So we will go straight on to the second set of presentations, first being from Noella Nibakuze from Mass Design Group, and then we'll have Tessa following after with the Q&A for the two presentations. So welcome, Noella.
Thank you very much. Thank you for inviting me. I hope the microphone is working well. Can you hear me?
Yes, I can hear you.
Great. Let me just share my screen. Can you all see my screen?
Yes, we can.
Just right. Yeah, good afternoon, everyone. My name is Noella Nibakuze. I'm an architect and also a design director here at Mass Design Group, based in Kigali, Rwanda. And I'm very happy and glad to be here and share this presentation with you all. I will start by introducing our company. So we are a design collective with more than 250 architects, landscape architects, engineers, writers, filmmakers, product designers, builders, and researchers from around the globe, representing about 20 countries. And I'm happy to present to you today all the work done by all these wonderful people. So one of our motto is that we are not architects to design buildings. We are architects to protect and save our planet, to improve the communities in which we live, and to awaken the links that bind us inextricably to one another. This is what Martin Luther King called the inescapable network of mutuality. So this drives all our work and designs. So today, the case study I'm going to present to you mainly is the Rwanda Institute for Conservation Agriculture, which is a new campus, not so new anymore, opened about 3 years ago, which is located in the east of Rwanda, which is a region that is quite hot and arid compared to the rest of the country. And then this campus was a project that was funded by the Howard Buffett Foundation together with the government of Rwanda, where they wanted to build, where they thought if they can manage to build this campus in this area and where agriculture can be done in this difficult area, then it can be done in the rest of the country, but also in similar locations like Tanzania or Burundi, our neighbors. So as for every project, we start by defining the mission. So for this campus, the mission of this campus was to train the next generation of leaders in conservation agriculture that attain healthy and sustainable food independence in Rwanda. From that, we had first on every project, we thought especially on this one, how can we reduce embodied carbon and operations carbon, starting from the very beginning that means the master planning. So the site itself is quite big, about 1,500 hectares. So how for us to be able to position these buildings on such a big site, we did a lot of research first. We looked at the water, all the lakes that surrounds our site. We looked at, for example, there's this savanna woodland, which we decided not to touch as it's a natural one. We also looked at all the areas we wanted to conserve and decided to place our buildings in an area that already had infrastructure, so that we do not disturb the area that has been conserved for a long time. So these are the tests we did at the beginning, and this was the resulting master plan, where we had student housing on the left of my screen, and then the campus or the classrooms and the labs on the western side, having everything connected by this middle spine road that is only pedestrians, also trying to face our buildings north, which was good because that was also where the lake was positioned. So we had the advantage of having a good view, but also orienting our buildings to avoid the west and eastern sun. So zooming in, why did we place our buildings there? Like I said, is the savanna forests that we kept intact, that we did not touch. We also looked at the existing buildings. They had asbestos roofs, so they were supposed to be demolished anyway. So that's where we placed our buildings. But we placed our agriculture-based enterprise or classrooms much closer to the lake, and had our animal-based enterprises to an area where the land was already disturbed, so that the cows and goats can graze in that area, like I say, without disturbing what is there that was natural. So the campus is divided into two scales. So we have the first year housing, what we call smallholder farmer, where the student actually experience the life of a typical farmer in Rwanda. And then as they move to their second and third year, that's when they start learning a value add and more enterprise-based agriculture and animal. So this is a typical first year housing. We planted all around where they can do their agriculture, and also have some animal. There was a barn. We orientated our buildings north-south, and also used as natural material as possible, and I will touch on this a bit later. So this is a typical section. Like I said, in terms of master planning and siting of the buildings, we really try to not disturb the natural environment as much as possible, but also we planted a lot of native trees so that we can retain all the water and avoid the erosion. Then the second part, the second scale, the enterprises or the classrooms are on the eastern side of the campus, connecting to each other. I think we realized that most of the time, especially the young people, don't think agriculture. They think it's not a proper, how can I put it? They don't value it as it should be. So we try to showcase agriculture in this building, and this is why they are elongated on this side. Yeah, so this is a typical section where, for example, as you walk through the campus, you can see where your yogurt is coming from. There's cow, there's milk, and then there's value add. Again, a section facing north. Some of the longer faces of this one faces east and south. So we try to clad with terracotta bricks, and also recess it so that we avoid the sun. That's why we have these big recesses on the east and western one, and also clear story facing north to bring in light and ventilation. yeah, again, a typical section which is similar, but again, really showcasing where our food comes from, so that everyone who goes through the campus can start appreciating the work that goes into that. A few images of the campus, which is completed now. The students are in. They are almost in their third year now. It's just 3-year bachelor degree. So these are all the first year housing with the bands and all the farming around the houses. So the next part, I'm going to talk about how, from the master planning to zooming in into the buildings, we really were intentional on following what the IPCC says, where we need to reduce the net emission of CO2 to half of current levels by 2030 and reaching net zero by 2050. And this is projects where we intentionally try to achieve that. So how did you achieve that? First of all, we asked ourselves, when they say half, it's half of what? So we know that buildings, about 39% of global total greenhouse comes from the building industry, but this is divided into operations and construction. So we need to reduce half of the emission related to operations and maintenance, but also half of the emissions of all future construction, and not only focus during the operation of the building. So when you compare operational and embodied carbon, you can see that operational is when the building is in use or being maintained, like from heating, cooling, electrifying. That's where our operational carbon goes. The embodied carbon, however, is throughout the whole life of a building, from extracting your raw materials to transporting to manufacturing, then from manufacturing you transport to site, and then during construction, and also during use, because you need to maintain and replace a few things, and also during the construction, and then to waste. So we realized that, yes, even though we've put a lot of efforts in the past, all of us in the operations, it was time also to think about how we build our buildings from raw to construction. So as you can see on this graph, embodied carbon in pink, which is quite high at the beginning of construction and to the end of when the buildings start being in use, and then also throughout the buildings for replacement and maintenance, and also end of life, where we realized that actually this inversion represents a paradigm shift on how we need to think about sustainability. So we need to also start thinking about low embodied energy materials and construction system, like structure system, and also to develop circular systems to build, maintain, and prolong the life cycle of our built infrastructure. So it's not only when the building is done, but how can you reuse for the circular systems, like I mentioned. So from that, we looked at all our projects from the past 10, 12 years to understand how we are doing against the global average, benchmarking, especially from the regions we work in. And that will help us to reduce embodied energy of all our future projects, and also establish benchmarks for the regions we work in. Because you can see on the next slide, when we started benchmarking our buildings, we realized that actually in Africa, there's no known benchmarking system for materials that we use. And we normally compare our buildings against, let's say, America or Europe systems, which could be maybe not as so accurate as we think. So from there, we also realized that in 2060, even though Africa currently we are not the ones building a lot, but in about 2060, we're going to have more current flow than any other continent. So if we are building so much, how do we ensure that we're actually building correctly and not damaging our planet, our environment? So from that, we worked with a local brick manufacturer. We can think that bricks are simple materials, but actually we worked with them to think about the embodied carbon that it costs for those bricks. This is a sustainable company where they use coffee husks to burn their bricks, and you can see that even though it's a simple material, it's quite a complicated way to understand what's in embodied carbon. So this research really did it because we wanted to understand. We want to have somewhere to start. Obviously, these numbers are not recognized, but it was for our own internal use. Yeah. So looking back, this is a building. This is the first building Massive and Group did, and it was in Rwanda, in the north of the country, a hospital where 10 years ago we were not intentionally building to reduce embodied carbon. However, we did ask ourselves questions related to the communities that we work with. So the Butaro Hospital, when we asked ourselves, can a building heal? And from that, we used only local materials that was from the region. You can imagine 12 years ago, not only transporting the materials there was quite hard, but it was also a good opportunity to really invest in local people and also try local materials. So we used earth from site. We used volcanic stone. It's an area close to the volcanoes. We used volcanic stones as well, where we trained local people in how to use it. And as you can see on this elevation, the stone is local and it was done by local people. So our intention was really to invest locally and to try local materials. That was the initial investment. However, when we calculated this building, we realized that our embodied carbon is half compared to similar buildings around the world, even though it was not our intention. And that really helped us to think of how we did it and how we managed it. And we realized that we did invest in our people. And this is a saying by Anne-Marie, who was a lead mason. Like no amount of value can be assigned to dignity. So buildings used by people in this area are the ones who really build them. So we reduced the footprint, but we also worked with the handprint. That means reducing the embodied carbon, but also elevating the dignity of the people we work with. How did you achieve that? We hired locally, sourced regionally, and invested in training, resulting in upholding dignity. So this is what we call low fab construction. We realized that locally fabrication construction, easily lead to reducing embodied carbon and operations carbon as well, which I will touch on the next one. So for RICA, which I just presented to you, which we did 10 years after Butaro, we were intentional on reducing our embodied carbon and our operation carbon at the same time. So this building question was like, can design improve human, ecological, and animal health? It's an agricultural campus. And for RICA, we actually went lower than half, where we reduced, compared to other similar buildings around the world, we actually were 2/5 lower, which means we even went lower than half of what is required by 2030. And how did we achieve that? So this is a typical section, business as usual on the left, and what we did at RICA. So foundations, we used stone foundations. We used walling, we used earth walling, and we used timber roof. And then we used terracotta roof, and everything was from Rwanda. So this is a typical section at RICA for all the 69 buildings we did, resulting to 12,000 square meters. So we used coffee husk, fired ceramic tile roofing, wood-framed roof structure, non-fired earth-based walling, that's CSTBs and rammed earth, and also stone foundations. So a few images of the timber we use. So all our roof structure, trusses, rafters, battens were made of timber, and a few columns as well. Some of the columns are concrete. And by using just timber via steel roof trusses, we managed to be 1/10 compared to that. So, and the few actually embodied carbon that was found in the timber, it was because of all the connections we had to use, not from the timber itself. So by using timber, first we really invest in local companies using timber. We also, as you know, deforestation is a big problem. So how do we help people using timber more productively instead of using it for firewood, and also replanting? So currently we are working with local companies to come up with guidelines to use timber as a structural material. Then we used earth, rammed earth. On the image below, you can see all earth was from site, and made from site as well, manufactured from site. They were all non-fired, which really, again, reduced the embodied carbon. So on this image, you can see by using CSTB vs other walling, we reduce our embodied carbon by half. And this really made up a big portion of our building, because most of the walls were structural as well. So CSTB took almost 25% of the entire building construction. And from working again locally, it was very easy to track our earth supply chain. It was from site. So again, really making it easier for us to calculate the embodied carbon coefficient, because we knew where it was coming from, we knew what the transport costed, and we knew what making it costed as well. Yeah, so all bricks were made on site in this shade by local masons, which really reduced our transport and cut down our CO2 emissions. So in yellow is where our site is, and 1, 2, 3, 4 is where we actually sourced our earth. But we also did a lot of tests initially to see where the earth is good, first for construction, but also that it's not going to damage by digging big holes, so that we don't actually leave it in a worse state than it was. So it took us almost 6 months just doing those research, and also seeing if the soil can actually stick and make bricks. So our engineering team really invested in that. So other than that, we also tracked our other materials, where it was coming from. Like I said, timber, soil, water, obviously, it was quite close. The soil, the laterite, this is what was used for all the earth, for the rammed earth and CSTBs. Going further, stone, aggregate, sand. Likely the region where we're building is also a region known for its stone and aggregate and sand. So it was, again, we took advantage of that to use these materials against others. Going further, cement, which is in the north of Rwanda, that's where we bought it. Ceramics in Kigali, again, not too far. We worked with local artisans to make all the windows and doors that were made of steel. Most of it actually made on site. Really, we were intentional on how we source our materials. But obviously, some things are not found in Africa. But it was a very small portion of everything we had, like the sanitary ware, the light fixtures, which came from Dubai or elsewhere. Yeah. We had solar panels, batteries that came a little bit further. The whole campus is solar, is using solar energy, which I will touch on it a little bit after. So as a result, 96% of Rika materials was excavated, harvested, and sourced in Rwanda. And not only that, 98% of Rika's labor were also around the Bugesera area or the East African area. I mean, the east of Rwanda area, not East Africa. We also worked with local manufacturers, cooperatives, artisans, and entrepreneurs to make all the furniture of the campus. I have a few images here. Literally everything from the chairs, the lamps, the flower pots, everything was done by local people around the country. Even the office chairs and all the cabinets, all the lampshades, all the decorations, which really significantly reduced our embodied carbon. I don't know what's wrong with this image. Just give me 2 seconds to refresh. I'll stop sharing for 1 second and then bring it back. Sorry about that. Yeah, so in addition to that, we know that by just reducing or minimizing the embodied carbon is not enough, but we also need to account for the future. So I might admit maybe we might not be able to do this on all projects, but for Rika, we actually planted native trees, 40 hectares of native trees, which will offset the greenhouse gas emissions, actually making Rika a climate positive by 2040. Like I said, and this is the map we developed for that replanting, really being conscious on using only native trees, and so that we can offset these offsets and become carbon positive. Actually, so it was not enough just to reduce, but also how do we actually bring in more oxygen, if I can say that. Yeah, so like I said, this is our buildings compared to the global average, and we're sharing this so that not only we can do this for our future projects, but also so that other people can do it as well. So when it came to operation, Rika campus is 100% off-grid, renewable power and water. So we use lake water for all our water consumption on the campus. It's filtered and reused for everything. And also we use solar power to power the whole campus. Obviously, Rwanda, we have a good climate. You really don't need much for ventilation or for heating. By using warm mass, it's easy to have a comfortable environment inside buildings. So we really had to really worry only about water and electricity, but also earth material was very beneficial to the comfort of these buildings. So moving forward, we are currently, because we could not stop there by doing this, but we want this to be adopted in Rwanda or the region. So we're currently producing a toolkit for the built environment to measure and reduce embodied carbon in Rwanda, where we have been working with ARUP, MAS, the University of Rwanda, and the Academy of Engineering, just to produce this tool, but also to train fellow practitioners to use it in their projects. In addition, we worked with the government of Rwanda to on the guidance on the use of Adobe blocks in the construction in Rwanda. So this was banned some time ago, but it was brought back again really for because it's an easily accessible material and easily usable, but also good for the environment. Yeah. So ending this on what we believe at MAS, that all construction design should be good, clean, and fair. And that really goes together from protecting your planet, but also for investing in your communities. Yeah, thank you very much.
Okay. Thank you very much, Noella, for that very insightful presentation. A quick reminder also to continue posting questions on the live chat. We'll quickly move on to the second part of the presentations from Tessa Brunette from ARUP. Welcome, Tessa.
Hi. Hi, Louis. Hi, everyone else.
Hi. Yes, please.
Okay. All right. Let me just work out how to share screens quickly. Sorry, that happened very efficiently from your side. So I'm going to catch up now. Sorry, I'm just trying to see share screen. Okay, it's coming. All right. Great. Thank you. So thank you for the invitation today. I'm here to talk about embodied carbon in Africa as part of this very important and interesting series. So what I'll be talking about today is a conversation in two parts. Really, it's around understanding embodied carbon calculations, but also understanding carbon factors, and specifically talking about the research that we at ARUP have done over the last year or so into identifying carbon factors for 5 African countries. So just a bit of scene setting to start. My name is Tessa Brunette. At ARUP, I am our sustainability leader for Africa, India, and Middle East. I'm an architect by training, although I haven't worked as an architect for many years, but I do very strongly believe that architectural skills are really helpful within the building industry. And in my role at the moment, what I really do is integrate and lead projects towards sustainable outcomes. That's a complete passion of mine. And I do enjoy the platform in terms of advocacy. I think that what we need to be doing and the extent of the change that we need to make in the built environment is such that we all need to be activists. And the platform is a really important one. So thank you for inviting us here today. I would just like to make a note that what I'm talking about today, especially the research, is a product of truly collaborative research within ARUP. I may be the person talking about it, but there are a lot of people behind, and this is only some of them. In fact, these are just the ones who've been involved most recently. But it's important just to remember that there are more of us. That I'm just the face. So a little bit about ARUP. We've been around for a while. ARUP is in fact Ove Arup's surname. He was a Danish guy and he was known as a philosopher engineer. And really his values were all about collaboration, integrated design, and sustainable outcomes. So that's very much what the company is still based on. And it's something that we all believe very strongly in. We are owned in trust, which also means that we've got no shareholders. So we're very fortunate to be able to invest our profits. Instead of having to pay shareholders, we are able to invest the profit that we do make into research, which is pertinent thinking about this particular conversation today, because we've invested quite a lot into identifying and progressing the embodied carbon narrative in Africa. In terms of ARUP itself, we're structured over 5 regions in the world. But in Africa, we're in 5 countries. So we have 6 or 8 offices in Africa, but we're in 5 countries. And we've been around for a while. So you'll see that the oldest offices are in fact Harare and Lagos that were established in 1951. So we've got quite a big legacy in Africa and one that we are very proud of. We're very based and completely subscribe to the UN SDGs. So understanding the full scope of that is really important. Today, we are talking about climate action, which is SDG number 13. But it's really important to remember for all of us that everything that we do here, all 17 UN SDGs, actually are around supporting the UN SDG number 1, which is no poverty. And that's particularly pertinent to us in the African context, because we are, and across the continent, we have such inequality. And really a goal for all of us as designers within the built environment should be to create dignified and equitable places for everyone in the world and everyone in Africa. That really is a focus. Lenses that we at ARUP use to guide our decision-making are around human health and well-being, zero carbon, circular economy, community resilience, social value, and planetary boundaries. So, in terms of the scene setting aspect, we all hopefully know about the urgency that there is in terms of the climate crisis around us. The IPCC report that was issued earlier this year was damning, unfortunately. It really shows that even though we've known in the last while, like decades, that what we are doing as a planet is not helping us, and in fact it's making our future worse, we're not changing that as a globe, as people around the world. So there really is an urgent need for action. And in fact, the IPCC said that we had at the time 30 months, and now we've got 27 months as a planet to keep the hope alive of maintaining the 1.5 degree maximum increase. And that's scary. And at the same time, it's a huge opportunity for us in the built environment to be making and shaping a better future. And just as a reminder, we are currently at 1 degree in temperature increase. So, and we see all of the extreme events happening around us and the impact that has on cities and communities and people. So 1.5 degrees, even that is quite a scary prospect. So what can we do within the built environment? Well, we all would have heard of the phrase net zero. That's certainly something that's been bandied about quite a lot. But what exactly is it? Well, in summary, what it means is that net zero is a state that's arrived at when the carbon negative aspects, the bits that extract carbon from the atmosphere fundamentally, are in balance with the carbon positive aspects. And so that what that means is the carbon emissions that we make. And in the built environment, what that means is that we reach the net zero state when all of the materials and all of the operational carbon that is produced during a building's life cycle is offset or is low enough that it reaches the net zero state. In terms of embodied carbon and why we should really care about that, well, it contributes a huge amount to that net zero balance that I've just described, but also the IStructD, which is the Institute of Structural Engineers, prepared this very interesting summary here, which shows and contextualizes the impact that we as designers, and particularly structural engineers and architects, can have in terms of embodied carbon emissions. So if we look at one return flight between Johannesburg and Nairobi, that's 1 ton of embodied carbon. But by saving 20% on a typical building, so just a regular 4-story concrete frame, type of building, by saving just 20% of the embodied carbon there, we can save 200 tons. So what we really need to be doing, was it 2,000? It's 200. What we really need to be doing is putting our energy into just saving that amount, and more, and doing better. The scope here for positive impact is really, really, really big. And just putting that into the context of a building's life, I'm going to go through this in a little bit more detail shortly, but this is also a diagram from the IStructD. And what they show here, when we look at the whole life carbon of a building's life cycle, it's the embodied carbon that equates to 50% typically of the whole life carbon over a building's life cycle. So there really is an urgent and important impact that we can have if we look at the embodied carbon. So whole life carbon is made up of 2 components, operational carbon and embodied carbon. In essence, the operational carbon looks at the bits of a building that can turn on and off. So that's looking at the power, the lights, the things that operate in the building over its lifetime. Whereas the embodied carbon typically are the things that you can touch. So that's the primary structure, which contributes to the most embodied carbon within a building, as well as, of course, all of the finishes and the installation within that building itself. There are some phrases attached to that. We must be wary of jargon, but there are lots of phrases that can be attached to the various portions of this whole life carbon assessment. Really what we're trying to do as an industry is move from cradle to grave. I know that this is what it says here, but also thinking about cradle to cradle, which is circular economy thinking, which I'm sure is the topic of another talk within this series. But what we look at when we look at whole life carbon is considering cradle. So that's where the beginning of a particular product or material is, like where it's mined, where it's planted, where it's the beginning of it, all of the processing, all of the transport, all of the installation, what it does over its life, and then how it's disposed of as at the end. And so that is a very honest and true reflection of the carbon emissions over that particular material and building's lifetime. I did mention jargon. We do need to be very wary of the risk of jargon with the carbon conversation. I would highly recommend this iStructD publication, which is called the Climate Jargon Buster. I would highly recommend that you have a look at that, because we must be quite clear with the words that we're using and make sure that we're using the right words with the right meaning behind them. But one thing that I do just want to identify is that in this conversation, when we're using the word carbon, it doesn't only mean carbon. In other words, it's not only CO2. That word must actually be used interchangeably to mean greenhouse gas emissions, because it's taking into account carbon dioxide as well as other greenhouse gas emitting gases, or other gases that contribute towards global heating, such as methane and water vapor. So it must just be considered interchangeable, just as a quick note. When we think about embodied carbon, and in the design process, it's really important to start from the beginning and understand where the biggest impact that we can have is. And to be quite honest, the biggest impact that we can have in embodied carbon is not to build anything at all. So when a client comes to you and proposes a new building that they want to build, we must be very, actually, it's quite hard, because obviously that's what we do. It's our job. It's how we enjoy ourselves and earn money. But it's really important to ask these questions, like, do you need a new building? Or what we see a lot in the global north is this narrative on building retrofit. So there in the global north, it becomes quite urgent and necessary to start looking at retrofitting. Of course, us in the global south and within Africa in our context, we there is an urgent need for buildings, but we do need to be very conscious when we're doing that. Then the next steps are building less. So do we need to have a 10,000 square meter building, or could we build a 4,000 square meter building and achieve the same outcome? Those are quite important questions. Then we start thinking about building clever, material reuse, low carbon materials. Then building efficiently. So that's saying, well, what we're building, we're going to use it smartly so that it's doing the most, instead of building in a very loose or kind of fat way. And then finally, the final step is minimizing waste. So that looks at how we build and the processes involved in that. Then it is really important to think about the biggest impact that we can have on a project and when that is. And of course, that is right at the beginning, during planning stages. So as designers, it's really important that we can be involved at the beginning of the project, because we can shape those decisions by the client, by the ultimate decision makers, and make the biggest impact in terms of carbon reduction. Of course, there's still improvements that can be made through every phase of the project. So we have to keep on trying every step of the way. In terms of the embodied carbon calculation, it is actually really simple. The principle of it is really simple. And I know that there's quite a lot of reticence and uncertainty around needing tools and wanting to understand what tool to use to calculate and which ones and what's available and what's free and all that stuff. Actually, we can all do these calculations by using pens and a calculator and a piece of paper. What it comes down to is multiplying the volumes of different materials on the projects by a carbon factor, and from that we get the kilograms of the embodied carbon, the kilograms of CO2 per meter squared in the building. This is what it comes down to. We must be very aware and conscious to keep the simplicity and not get tied up in complexity. So just tying in with my earlier observation around timing, we need to also be doing these calculations throughout the process. So it's quite important to understand at the beginning of the project, we can achieve the most impact, but the accuracy will be the least because it's the beginning of a design. So as we go through the process, we lose the ability to influence the whole life carbon of the project, but our calculation will get more accurate. So the important thing here is just remembering that this is a completely iterative process. We need to start. We must start at the beginning and we must redo the calculation. And this is when things like tools do become useful because you can just change the factors slightly. I mean, not the factors, the volume slightly as your design changes, but fundamentally the calculation remains the same, the process from the beginning to the end of the project. So that was the scene setting. Now I'm going to talk a little bit about the actual embodied carbon calculations themselves and talking specifically to some projects that we've worked on. So the slide that I showed previously, this is just extending out on that. In essence, this is a simplified embodied carbon workflow. We start with the inputs, which are the volumes. We need to understand the materials and the volumes of those materials in the various buildings. Then we do the calculation by inputting the carbon factors. Then we get the result. So we press equals and it comes out with a number. And then at the end of that process, we need to understand, well, so what? What does that number mean? And we use that number to benchmark against other projects and what we understand to be industry norms, and ultimately start back at step one again and make it better. So we need to be using these outputs and the benchmarking process to then ask ourselves, well, how can we do better? How can we reduce the carbon on this project? And where are the places to focus? So this is a South African residential building where we have conducted an embodied carbon calculation fairly recently. And what I want to do here is just take you through the process really quickly, just so that you understand a bit more about what that means. So again, using the simple workflow, what we did is we calculated the material volumes, and we did that by manual calculations, because literally it's volumes of materials. We can use BIM generated Revit schedules, for instance. We can use all sorts of software to confirm what the various volumes of the materials are. And of course, quantity surveyors are often a good source of information for volumes because it's their job to be calculating what the volumes of things are of the different materials. Then the second step is going through the calculation factor. So there are various stages in this, which I showed very briefly earlier on. I'm not going to go into too much detail on that, but in essence, what you do is you take the inputs, as I've said, you input the carbon factors into that, which differ country by country, but I'm going to talk about that a little bit later. You add the transportation and the construction waste component, and then you get an output, which is the total kilograms of embodied carbon per square meter against the gross internal area. So that's important. So we need to understand the total tonnage with the gross internal area. Then we use those outcomes to benchmark. This really, as I've said before, and I'll say it a lot, is the most important part of this process, because it's only once we understand what this number means in terms of benchmarking that we can then start at the beginning again and do better. So this is a screen extract showing the Revit model. In this instance, it was a Revit model. We've only done the carbon, well, this particular calculation here is for this particular building, which was a residential building, as I've said. It's a 4-story building overall and concrete frame with PT slabs. So we did lots of manual calculations for this particular building because we're all busy learning and we're going through the process. What I really try and reinforce with my team is we need to start with the manual calculations, because that's how we learn and how we understand the process. So this is an extract from the spreadsheet that shows the different volumes. So you can see here what we're doing is just multiplying width by depth by height and getting volumes of stuff, of the different materials. Then the second step is we put those volumes into a calculator. And again, this is a particular tool, but there are loads of tools available. This happens to be an in-house ARUP tool, but there are loads available, and they are freely available as well. But also, you don't have to use the tool. It can be a hand calculation. Don't let that hold you back. And then we get the outcomes. So on this particular project, what you can see here is that the bulk of the project or the bulk of the material and the embodied carbon actually sits with concrete. So we've got 96% of the materials by mass is concrete. So without going into too much detail, what we can see right away and start informing our design process is that if we want to reduce the embodied carbon on this project, what we need to be doing is reducing the tonnage of concrete. And so then we can use that to inform our design decisions. So we then start at the beginning again and say, well, how do we reduce the amount of concrete? And it's volumes of concrete, as well as then doing smart things like changing the actual concrete mix, for instance, in this particular example. So the benchmarking process is really really useful, which I've mentioned earlier. In this particular instance, this design was towards the lower end of the typical range for residential buildings, and this is a global benchmark. Just by the way, we don't have enough data at the moment, and when I say we, I mean as an industry, we don't have enough data at the moment to have an accurate Africa benchmarking yet, but we really do need to get there, and that's what we all can contribute to. So this particular building was towards the lower end, but that does not mean that that's a good place to be. We can do a lot as well to be driving that lower. There is also a scores, what's this thing called? Summary of a ranking of different types of building, which also helps to benchmark. And so this can be used. And again, what this is showing here using this particular benchmark is that it's on the, it's a typical mid-rise for this particular building. But again, constant room for improvement. So there are some other case studies that I'm going to talk through quite quickly, just in terms of guidelines around where are the opportunities to be reducing carbon on all of our projects quite quickly. So this is an example of a distribution warehouse that we worked on. I can't recall which country, but here what we did is there was a long span steel structure, which meant that we needed nice big chunky steel sections to support that. And what we did by early upfront quick carbon calcs, quick and dirty, we identified that we needed to reduce the tonnage on that steel in order to reduce the carbon. So by reducing the spans of the various steel members, we were able to reduce that and reduce the carbon quite significantly. And this was an early decision. This was during the planning stage of the project, so really early on in the design process. There are other opportunities, of course, where through the initial assessment. So it's really important to identify the structural efficiency and do things like reduce transfer slabs, for instance. Transfer slabs are there to achieve architectural and client-related outcomes. If the structural engineer were to lead the conversation, there would be a regular grid, and that grid would carry through the entire building without any transfer. The most efficient from a structural perspective, and therefore a cost perspective, and therefore a carbon perspective, will be the grid that continues straight through. But that's a conversation to have, of course, with the architect, and that's what we need to be talking about in all of our projects. Oops. So that talks to the grid spacing. It's just a quick note on this. Basements take up a lot of carbon, and where we can, we really should be working to reduce the extent of basements and any retaining structure. yeah, that's quite important. There are, if then also you think about embodied carbon within the context of reduce, reuse, recycle, and recover, so the 4 Rs, really what we must be doing is limiting the carbon intensive materials. We need to be actively seeking lower carbon alternatives, which we saw in the previous talk. There's a really wonderful response to the local context as well as alternative materials. Finishes are often somewhere where they don't contribute to a massive proportion or percentage-wise of a project's embodied carbon, but they can have a very significant impact if we reduce them, if we just omit them. So that's something to think about within the design. Using recycled materials and reusing materials are really helpful. And of course, minimizing waste and using alternative materials. So we have a project where we've used single-use plastic pushed into Coke bottles, plastic Coke bottles, as void formers instead of virgin hydrocarbon, which is quite an interesting way to think about reducing embodied carbon. In terms of the design, there is this balance between adaptation, or the ability for a building to be easily adaptable, alongside its longevity. So providing flexible spaces is really important. So we need to be designing lean, but at the same time, we need to be designing smart. So making sure that the building's not so lean that it can't ever perform another function, but ultimately reusing the building, so building less, minimizing demolition and repurposing is really helpful. Prefab and thinking about design for disassembly is also useful in terms of the last step of that embodied carbon pyramid. But all of these options must and should be explored iteratively throughout the design process to try and make sure that we get to the lowest embodied carbon. So the second part of this talk is going to be around research that we have done into country-specific carbon factors for Kenya, Mauritius, Nigeria, South Africa, and Zimbabwe. So just a reminder of that process. So if we look at quantifying the project carbon and the carbon factor, it's through these two aspects. So this is the volumes and this is the factor that we multiply in order to get the embodied carbon per square meter. This is the process that we're talking about now, just as a reminder. And of course, now we're talking about carbon factors themselves, and a reminder that this is always an iterative process. So carbon factors, and what does that mean? A carbon factor is basically it's a factor, it's a mathematical number that is applied to the energy use to represent the equivalent carbon emissions associated with that. So a carbon factor is something that's prepared for instance, for a country that you could use for a particular material in a particular country, that you then apply to your volumes to then understand what that means in terms of the total embodied carbon per square meter. And these are always reported in a carbon dioxide equivalent, so that's the CO2e, remembering that carbon is used like interchangeably, and so you must remember that actually this does include greenhouse gas emissions, so as an example of that. One of the things that we see across the world in terms of carbon factors, and this is a diagram from iStruct again, is that there is not a lot of data available on carbon factors around the world. And in fact, where we are in our context is that there's a great glaring hole of an entire continent of 54 countries where we don't have any local carbon factors. So what we find is that what we use aggregated data. So we're typically using carbon factors that come out of the UK, but in reality, those are not going to be completely accurate. So there is a journey for us to go on in terms of being more clear and being more accurate about what those carbon factors are. However, saying that, carbon factors around the world are generally comparable. The difference tends to be differences between the transportation of the materials. So the distances that the different materials need to travel. And when you think about that, it's like, where the material is mined, for instance, and then it travels to a processing plant, it then travels to another processing plant, and then somewhere else across the world to get turned into, like from iron ore going into steel. Every single time something moves like that, that's added onto the material flow, and it's those carbon factors that will contribute, or that material flow that will contribute to a different country-specific carbon factor. What we see is that steel, for instance, tends to be equitable around the world, but where there are local market differences, where there are materials that tend to be sourced largely in country, such as bricks, for instance, there actually is quite a lot of variation. So a key thing here for us is to understand, and for each of us is to understand the material value chain in country, and to just think about what the transport component is. And even in the absence of calculation and the absence of carbon factors, we can be using our best judgment to reduce excessive transportation wherever we can. Then, in terms of the benefits of carbon factors and country-specific carbon factors, having these factors will become increasingly important as the calculations become more used. So this is looking ahead. So what we really need to be doing now is gathering the data and using this to create more accurate carbon factors, but most importantly, getting familiar with actually doing the calculations in the first place. And I also just want to reinforce that not having a specific carbon factor for any country in Africa or the continent as a whole should not be a barrier to conducting the calculations in the first place. Because the carbon factors are generally equitable, there is a relational benefit to doing the calculation. And it's only through doing these calculations that we become familiar with it, and then we can start making better design decisions. So in terms of our own research journey, we have recently completed 2 pieces of research into carbon and carbon factors in Africa. So the first one we did was around material flows. In essence, what we did here was look at the typical materials in our contexts, where they come from, where they go to, and how they're processed. This is what I described earlier. Moving on from that, the second piece was then quantifying the carbon involved in obtaining and processing those materials and making it more specific by developing country-specific carbon factors. We're currently in this phase. Well, actually, I should say, one of the findings that I'm going to talk about is that we weren't able to gather enough data in this process to be completely confident about the carbon factors that we created. So we're now in a phase where we're combining these two. We're looking at the outcome and this process in carbon factors combined with doing and conducting the calculations, which is project-based research, to iteratively improve these carbon factors. So we're using the data that we get from our real-life projects, plugging them back into these calculations, and arriving at more and more and more accurate carbon factors for each country. Then what we do is use this to benchmark. So we then as an industry would be able to benchmark our projects across the continent and understand where we're able to make better decisions. And of course, this all feeds into whole life carbon assessments on all building projects. But both of these processes can actually happen now, can and should be happening now. So I'm going to talk very briefly about the Kenyan specific research that we conducted, because this is, of course, an event that's hosted by the Kenyan Green Building Society. I do just want to identify that the 2 Kenyan colleagues of mine who may be on the call today, I'm not sure if they were able to join, are Caroline and Jeffrey. They both sit in our Nairobi office and were intimately involved in this research, and I would encourage those of you in Nairobi or East Africa in general to reach out to them and have a conversation with them about embodied carbon. They've got a lot of input to add. So our colleagues in Kenya, we went through the process of conducting this carbon factor research. What we started off with was identifying the key materials that we looked at. So we looked at concrete, steel, and bricks, and in essence, we found out where they came from, where they go to, how they're processed. That is the basis of the carbon factor calculation. We then used that information to prepare the factor, considering the local energy mix, and arrived at an outcome. But what we found really interesting in this process was that there's very low awareness of embodied carbon factors across the construction industry. So we weren't able to actually get enough data, to be quite honest around that. And there was also a reluctance by the manufacturers and suppliers to share their information, especially related to the energy data, so the energy usage that they have when processing their various products. It was also quite difficult to identify the sources of the different raw materials. And of course, because there is no country-specific energy factor for Kenya, that was a difficulty as well. And it was difficult just to follow the different processes. So we did do calculations for Kenya, and we used a lot of assumptions. But one of the things that I'm going to be talking about is the need for this to increase and to be done more. And of course, for us as an industry to work together to do that. So in doing this again, what we would like to be doing is working very closely with industry, and that's industry from across the board, from designers, engineers, architects, to the building owners, to the actual building and construction material industry. The result is that we've got quite a low factor or low confidence in the accuracy of our data, because we had to borrow a lot of information from the UK database. Also, that's because the amount of wastage and energy input into the production process was largely unknown, because we couldn't gather that data. So if we put that alongside our Africa-wide interrogation, you'll see that much of our confidence in terms of the various materials across the countries is quite low. So we got a fairly good level of confidence in Mauritius, and fairly good in South Africa as well. But in countries, especially in Nigeria and Zimbabwe, and partially in Kenya, we weren't able to reach a state where we were happy that we had enough data to be actually confirming a carbon factor. So what that means for us as an industry is that, and also for us as ARUP, is that what we're doing, as I mentioned before, is gathering the actual data from real life projects, because that's when our structural engineers and architects are most empowered to be having a chat with the various suppliers and a chat with the builder, and having all of those conversations during the construction process, and getting honest answers about where the materials come from, where they're going to, how they're processed, and how much energy is used in that. It's much easier when you're actually working on a project and you have relationships with people that you're working on. Then that data would be fed back into the calculations, and we would use that to develop more accurate location-specific carbon factors, all of which the ultimate goal is to help us all to make better design decisions. So now I'm just going to have some closing thoughts. So I've touched on this a little bit, but I do want to reinforce the importance of collaboration in terms of where we as an industry need to get to. We aren't going to get there if we work in silos. So it's absolutely critical that we start to and really start and continue and try to work together as much as we can. And so again, I have to say thank you for this platform, because it's a really valuable one for us to talk and learn and start sharing information with each other. The green building councils and societies across the continent have a really important role to play, and they are actively playing that role. So we have Louis here today, who's convening this session, and across the continent there are other of those organizations, as well as the World Green Building Council, who are seeking to play an active role in this space. We really need for everyone to be gathering data and finding a collaborative platform to share that data, so that we can start creating the most accurate carbon factors for our calculations. I do just want to make a quick distinction, because I have had questions in the past about certification. So like, for instance, a Green Star certification or LEED or BREEAM, and embodied carbon factor calculations. They are different things. So please don't get them confused. It's not the same thing. However, and at the moment, most of the certification tool sets don't include an embodied carbon credit in them, but that's changing. And we're actually working with the Green Building Council of South Africa at the moment to try to identify how we could do that. We're working with other with loads of people in industry to develop a credit within the South African context, and that then would be rolled out across Africa. So we as an industry must all be 100% part of that, and we're also talking with them about how the role that they could play as the World Green Building Council and the African Alliance to create a platform for sharing this data about for the various materials, and then also, of course, what that feeds onto carbon factors. There are a number of useful links. I don't think you can click on this, but perhaps if we share the slides, you can. But there's loads of content available online, and I would really encourage you to read that, to listen to the various webinars that are available. iStrike, for instance, has a load of stuff, and it's phenomenal. Some of the YouTube and I'm sure Share Your Green Design have equally valuable resources available, but there's a lot available there, and I encourage you to read it and listen. And then in closing, I think I've said it quite a lot, but I'm going to say it again. The most important thing is to start calculating. Don't wait. The tool is not important. We can do this on a piece of paper. There are loads of tools available online. Just remember that the basic premise is it's volumes of materials times by a carbon factor, which is also readily available. And don't stress too much about the carbon factor equals the embodied carbon per square meter. Let's all share knowledge and information and really try to learn from each other so that we can maximize the impact that we need to have in order to make sure that our future and our children's children's future is as good and amazing as it possibly can be. So on that note, I will stop sharing and open the floor to Louis, who will facilitate questions. Thanks.
Yes, thank you, Tessa. I think that was a very thorough. Hope you can hear me now. Yes. Thank you for the rather thorough and informative session.
I can't hear. I don't know if that's just me or anyone else.
It should be.
I'm muted. Sorry, I'm unmuted myself now. My apologies.
No worries, no worries. So yes, thank you again, Tessa, for the rather thorough and comprehensive presentation. Really enjoyed it. The interest of time, I think we'll jump straight into the Q&A session. And there are a couple of questions that have come in for both speakers. First question being for Noella. Do you think the community appreciates the value of using local materials and construction techniques?
Yeah, that's a good question. I think it takes time. We've been doing this for the last 10 years. And initially, I mean, like the Butaro Hospital, I think it's a very appreciated place. The communities themselves, they do appreciate it. But I think people maybe from the cities are the ones who don't understand why we should not do things like buildings from Dubai or wherever, which is that people can find easily on the internet. But I think it takes an educative way of educating people, and as the time goes, they start to appreciate it, especially because this is things they can also replicate themselves, that are cheaper and easily accessible. So it has taken time, but now we can see the result of really everyone appreciating it and wanting to do it for themselves, because I think these local materials, you normally see them in these very expensive hotels for tourists to come and experience Rwanda or Africa. But I think now even the locals are understanding that it can be done by anyone.
Thanks. And also just to add to that, I think the case study that you had given with the campus, Rika campus, if I got that correctly, really goes to show how possible it is as far as using the local building materials to reach net zero target. So next question for both speakers, for both Tessa and Noella. What would be your key recommendations for architects and engineers from a sustainability point of view working in Africa?
Shall I start? I think the thing that we really need to be doing is asking questions. I think that quite often what I see across my colleagues is that people make an assumption that the client will say no before even asking the question. And so while we may have all of these great ideas in our head and knowledge that we're eager to share and boundaries that we really want to push, we hold ourselves back by not proposing them. And so my suggestion would be we have to start asking the questions. We have to start learning how to be brave enough and build our own confidence to ask those questions. And it doesn't have to be in an abrasive or aggressive way. It can just be, this is about working together, and it's about us working with our clients ultimately to shape a better world. That's really what we're trying to do, improve our built environment.
Cool. Thanks, Tessa. Yes, Noella, you can go ahead.
Yeah, I can add on Tessa. I mean, I agree with her. I think also as architects and engineers, we do appreciate sustainability, but we do not think we can do it ourselves. I think we need to understand that sustainability is not a style or an aesthetic things you do or don't do, but it's really required. It's a must. It's like having, I don't know, I can give you like you need to have your toilets in a building. Like that's the same for sustainability. Otherwise, we're already behind on doing this. So I think if we realize and understand that it's just a must and not an option, then we'll do it.
Great. Great points from both of you. So moving on to the next question. I'm assuming this is going to both speakers. Would a better education on vernacular architecture for both designers and the wider public be beneficial? We can start with Tessa.
Yeah, I think awareness and appreciation of how people build things just normally is really important and valuable. I think it also Noella, what you said earlier about like importing a Dubai design just because it's fancy and flashy and glass and all that, it doesn't make it appropriate. It doesn't make it nicer. It just makes it flashy. And I think that valuing how people build already, like, it's a hugely valuable thing. And so I think it's a combination of awareness and education, as well as appreciation and like recognizing the value. I think that's quite an interesting one. So yes.
Yeah, I would say yes as well. I mean, definitely. I think we need to really showcase and add value that vernacular architecture has, and instead of thinking that it's part of our history or that it's something that is not in trend. And that really starts in school, in education, but also as an intern or in offices, really bringing back that value, but also really like what you're doing, Share Your Green Design, really showcasing these projects in Africa or around the world, where actually people can access that. I think there's a lack, especially in the education system, of vernacular architecture in general, and that's something that everyone should invest in.
Great stuff. Great stuff. And so those are the only questions we had for the Q&A session. So in closing of this session, and also it's quite interesting to hear some of the work that's going on with South Africa, and also hopefully in the future we'll be able to add on that. So I'm not sure if you've heard, Tessa, of the IFC Edge rating tool. Those are one of the tools that we've seen, especially that we use in the country, that uses embodied carbon. That measures embodied carbon, and I thought it would be also really interesting to look at as you're continuing your work with South Africa as well. But anyway, just to mention, thank you again for your very informative presentations, both Noella and Tessa. Thank you for your time, and then we can now proceed to the closing session. So I'd like to invite back Andrea Ruíz, who, an interesting fact, is also the business and technical advisor for Share Your Green Design. So we'll start with her closing remarks and then move on to Cecilia Wandega from CSTI, and I'll be closing on behalf of KGBS. So the floor is yours, Andrea.
Thank you very much, Louis. Well, is really great to arrive to the end of our webinars about digital tools for green building designs. We have worked together with the Center for Science and Technology Innovations, or so-called CSTI in Kenya, which supports science-driven environmental initiatives to stimulate the development of new technologies, promote sustainable business innovations, and enable community-led growth all across Africa. We also welcome students from the Kenya's Green Building Society, also called KGBS, and we have learned about Share Your Green Design's ethos about sharing knowledge to help the construction industry to reduce carbon emissions. We touch in many subjects and on these different webinars, and some of them are the whole life carbon, where we provide an introduction about what this is, and we have demystified the process of the calculations. We also saw a few specialists talking about the life cycle analysis. We learn about various different digital tools that can be used for the calculations of a green building, such as CANDI-2, IES, Revit, Dynamo, etc. We have touched upon the digital twins and how important they could be for the development of a complete city. And finally, we have learned about sustainable materials and how some of the speakers we had, for example, from 2050 Materials, are sharing the information so we can use them. Now, from the, not sure if you can hear me well. Okay, so more than anything, we have given examples of case studies and different projects that have been using these tools or these methods, and that are also using local materials, not only in Kenya, but all the way around the world. So with this, I would like to say thank you to the speakers who have very kindly joined us for these teaching sessions, and for all the moderators who have also been part of this, additionally to the CSTI, KGBS, and every single person who have made this possible. Well, we are closing the first series of Share Your Green Designs webinar, and I want to let you know to just go over to shareyourgreendesign.com, where you can keep up to date with the latest in sustainable architecture, engineering, construction. We have various different tabs about research, news, events, podcasts with many other specialists on the industry, competitions, students' work, jobs, and we would love to have you as a visitor and a contributor. So stay tuned for future events from Share Your Green Design. Thank you. Over to you, Louis.
Thank you. Thank you for your kind words, Andrea. So moving on to Cecilia.
So I want to thank everybody. This has been a phenomenal, and for those who don't know, the whole idea for this was a genesis. We collaborated before with KGBS and the International Sustainable Collaborative Center from Germany on circular plastics and building materials. And after Share Your Green Design saw that material and understood there was a need for going deeper into the practitioner space, not into the chemicals itself, they helped coordinate and bring this together in the space of about 2 months. And as Andrea said, there's been an amazing amount of information, getting a lot of good feedback in terms of everybody saying each of these is 3 sessions, and I'll probably need 3 weeks to go through each session. And what I wanted to do is then open this up for, as a research institute and Think Hub, we love to bring people together. So if you could let the Share Your Green Design team know if you're willing to collaborate on the ideas that were shared during this, we're working towards creating a digital collaboration space. The CSTI focus will be looking a lot at chemicals in construction and their biodiversity impact. And we want to have different perspectives on that. And you've already seen issues on ventilation, issues on lighting. We'd now really like to go on the environmental impact side. So opening it up, please let the Share Your Green Design team know if you'd want to participate on an ongoing basis, and looking forward to more. Thank you.
Great, thank you. So I guess I'll be closing the session. And firstly, I'd like to thank CSTI for ongoing partnership and also considering us as for part of this initiative as well. And also on our shared mandate with the Share Your Green Design team on creating or building capacity and demystifying what it means to design and build green. Hopefully, also from the sessions that we have, not just this one and also the previous 3 sessions that were there before, you'll be able to understand within the different disciplines what exactly it entails, how these tools that were showcased in the different sessions contribute to or help with data-driven decision making at the different stages of the life cycle, and also understand that the life cycle of a building doesn't just end at the handover stage into operations, but all the way to the end of its life during demolitions, and also encouraging a circular model for operating and our constructing and operating our buildings. I'd also like to echo Tessa's final words again. All of this transformation within the built environment is only possible through collaboration, and from different parties coming together, sharing what we have is the only way that we'll be able to give the impact that we're looking to achieve within the industry itself. So thank you again, everyone else as well, and have a lovely time. Thank you. Bye, everyone.